We often imagine black holes as the ultimate monsters of gravity, swallowing everything that dares to drift too close. They are the pits of eternity, the places where light itself surrenders. But what if this terrifying picture is only half the truth? What if behind the mask of the black hole there lies a different creature stranger, subtler and perhaps even more unsettling? This is where the story of Gravastars begins, an idea born not from science fiction, but from the attempts of physicists to fix the cracks in our understanding of the cosmos. For decades, the singularity at the heart of a black hole has been a mathematical embarrassment. Infinity is not supposed to appear in the natural world. When equations give infinities, they are really telling us that our theories are incomplete. And yet black hole theory asks us to accept that the core of a collapsed star can shrink to a point of infinite density, where the known laws of physics collapse in on themselves. Some of the greatest scientific minds of the 20th century struggled with this contradiction. Albert Einstein himself doubted whether black holes could be real. Later thinkers like John Wheeler, Roger Penrose and Stephen Hawking turned them into pillars of astrophysics, but the discomfort never fully went away. A singularity was a mystery too sharp to ignore. It was in the early years of the 21st century that two physicists, Powell Mazur and Emile Mortola, proposed an alternative. They suggested that when a star collapses under gravity, the process might not always end in a singularity. Instead, something extraordinary might occur. At the moment when collapse should produce a black hole, space-time itself could undergo a transformation, a kind of phase change similar to water freezing into ice. Instead of forming an infinite point, the star's core could transform into a bubble of vacuum energy, an exotic substance that physicists already believed was driving the accelerating expansion of the universe. Around this bubble would form a shell of matter so dense and so unusual that it could hold the structure in perfect balance. This object would be called a Gravastar, short for gravitational vacuum star. From far away, a Gravastar would be almost indistinguishable from a black hole. Its gravity would bend, light its presence would anchor the orbits of nearby stars, and any gas falling toward it would heat up and shine in X-rays. But inside it would be something radically different. No singularity, no event horizon in the traditional sense, no point of no return. Instead, a hollow heart filled with a repulsive push of vacuum energy, wrapped in a shell thinner than a hair, yet carrying the weight of an entire star. The outward push of this energy would perfectly cancel the inward pull of gravity, leaving behind an object that sits forever on the razor's edge of collapse. Think for a moment about how strange this balance really is. Imagine a balloon. The air inside pushes outward, the rubber skin holds it in. Now replace the air with the most mysterious energy in the cosmos, and the skin with a layer of exotic matter that resists collapse with negative pressure. Something ordinary matter can never do. Scale it up to cosmic proportions and you begin to glimpse the architecture of a Gravastar. To human imagination it feels almost like a cosmic trickster, a star wearing the mask of a black hole but hiding a hollow secret within. If such objects exist, they would not only rewrite the story of stellar death, they would also address some of the deepest paradoxes of physics. Black holes seem to erase information, destroying the record of everything that falls into them. Quantum theory says this is impossible, that information cannot be lost. Gravastars may offer a way out of this contradiction. With their physical shells and vacuum interiors, they could store or preserve information rather than erase it, keeping the laws of physics intact. In this way, they might bridge the gap between general relativity, which governs gravity, and the large-scale universe, and quantum mechanics, which governs the microscopic world of particles. Two theories long at war could find common ground inside the hollow heart of a Gravastar. This possibility alone makes them irresistible to theorists. Yet it also makes them haunting. Because if Gravastars are real, then we may have been fooled all along. Every supposed black hole we have detected could in fact be a Gravastar in disguise. The monster we have feared may not exist. Or worse, it may exist, but only as one face of a deeper and more complicated reality. For much of the 20th century, the black hole seemed untouchable, a perfect prediction of Einstein's equations and a reality confirmed by the motions of stars, the bursts of X-rays in distant galaxies, and finally the haunting image captured by the Event Horizon Telescope in 2019. It was a picture that matched theory with breathtaking accuracy. A dark circular shadow surrounded by a glowing ring of light, a silhouette of gravity itself. To most astronomers, this was the ultimate confirmation that black holes were real. But to others, it raised a troubling thought. If we can only see the shadow, the effect on the surrounding matter, how can we be sure what hides inside? Could it be that nature has given us something that imitates a black hole so perfectly that we cannot yet tell the difference? That is the unsettling promise of the Gravastar. Outwardly, it behaves like a black hole. It curves space, it swallows matter, it anchors orbits and creates jets of energy. But inwardly, it avoids the most terrifying feature of all, the singularity. Instead of crushing matter to a point where the laws of physics collapse, it replaces that doom with a bubble of vacuum energy. This change may seem subtle on paper, but its implications are enormous. It means there is no event horizon in the traditional sense. There is no boundary beyond which information is lost forever. What falls toward a Gravastar might interact with its shell, might leave subtle traces, might not be erased from the cosmic ledger. To understand why this matters, we must revisit the information paradox. In the 1970s, Stephen Hawking showed that black holes should emit faint radiation, a slow leak of particles that causes them to evaporate over unimaginable timescales. But if that radiation carries no memory of what fell in, then information would be destroyed. And yet the laws of quantum mechanics insist that information must always survive, no matter how scrambled. The clash between these two principles created one of the deepest conflicts in modern physics. Gravastars offer a way out. With no singularity, no horizon in the strict sense, there is room for information to persist, perhaps encoded in the exotic shell or reflected in the vacuum within. This makes the Gravastar not just an alternative model, but a possible bridge between two rival empires of science. General relativity describes the large-scale stage of the cosmos, the bending of space and time, the collapse of stars and the orbits of galaxies. Quantum mechanics describes the microscopic theatre where particles flicker in and out of existence and probability rules. For decades, these two frameworks have resisted unification. Black holes with their singularities are the battleground where the conflict is most violent. Gravastars could be the peace treaty, a structure where the mathematics of relativity and the principles of quantum theory coexist without contradiction. Yet the idea is controversial. Critics argue that exotic matter with negative pressure may not exist in the forms required. They point out that black holes are already supported by mountains of evidence while Gravastars remain hypothetical. But the counter-argument is equally strong. Black holes have never been observed directly. What we see are effects, shadows, motions, and radiation. The monster itself has never stepped into the light. If appearances can deceive, then perhaps the universe has been disguising its true creations all along. Picture for a moment the centre of our Milky Way. There lies a dark mass 4 million times heavier than the Sun, known as Sagittarius A star. Stars whip around it at breakneck speeds, invisible hands pulling them into tight curves. To astronomers, it is the smoking gun of a supermassive black hole. Yet from another perspective, it could be the throne of a Gravastar, a hollow sphere of vacuum energy, cloaked by a shell so thin and so dense that it might as well be invisible. Both scenarios fit the data. Both explain the orbits and the radiation. Only the interior story is different, and until our instruments sharpen to an almost impossible degree, we cannot be certain which tale is true. The consequences of either answer are staggering. If black holes are real as described, then our physics is incomplete. Our theories broken at the edge of a singularity. If Gravastars exist instead, then the universe has found a way to avoid infinities to preserve information, and to offer us a glimpse of a deeper lore. In both cases, the cosmos is stranger than we imagined. In both cases, the darkness at the heart of galaxies hides secrets that challenge human understanding. And so the debate continues, not just in equations and telescopes, but in the imagination of anyone who dares to ask, what truly lies at the edge of collapse? The story of the Gravastar cannot be told without stepping back into the last decades of the 20th century, when black holes were already moving from the realm of speculation to the realm of evidence. In the early years after Einstein's theory of general relativity, black holes seemed like mathematical curiosities, odd solutions to equations that even Einstein himself doubted could exist in nature. But by the 1960s and 70s, the evidence began to build. Astronomers observed stars orbiting invisible companions, saw X-rays erupting from hidden sources, and pieced together signs of compact objects that could only be explained by collapse beyond the point of return. By the end of the century, black holes were no longer whispers. They were giants accepted as real players in the cosmic drama, yet this acceptance never silenced the questions. Physicists disliked the idea of singularities because singularities were not solutions but failures. Mathematical white flags signalling that our theories had run out of power. To believe in black holes was in some sense to admit that physics ended at their core, and for many thinkers that was unacceptable. Nature, after all, had always shown a tendency to preserve order to hide deeper laws where old ones seemed to fail. Why should gravity, the most universal of forces, suddenly break down at the heart of its own creations? It was against this backdrop that Powell Mazur and Emil Motola introduced their daring hypothesis in 2001. They asked a radical question. What if black holes do not exist at all? Or at least not in the way we think? What if every so-called black hole was in truth a Gravastar, a hollow object stabilized by vacuum energy and cloaked in exotic matter? In their model, the collapse of a star is not a march toward infinite density, but a transformation of state. Just as water turns to ice or steam depending on pressure and temperature, so too might collapsing matter trigger a phase change in space-time itself. The crushing inward pull would give way to a bubble of vacuum energy, a repulsive core that halts the collapse before a singularity can form. To imagine this picture the death of a star many times heavier than our sun. For millions of years it shines, fusing hydrogen into helium into heavier elements, each stage building a more massive and unstable core. When the fuel is exhausted, the delicate balance collapses. Gravity surges inward, atoms are torn apart, and even neutrons buckle under the pressure. In the traditional picture, this collapse continues unstoppably until a black hole is born. But in the Gravastar scenario, something else happens. At a critical density, quantum effects and vacuum energy intervene. The interior undergoes a sudden transformation. Instead of compressing into a singularity, the star's core blossoms into a region dominated by negative pressure, a bubble that pushes outward. Around this bubble forms a razor-thin shell of exotic matter, the skin of the new star locking the structure into stability. This is the Gravastar, not an abyss but a bubble, not an infinite point but a hollow chamber of vacuum energy. Its shell holds the mass, its interior holds the mystery. And from the outside, the deception is complete. Telescopes see an object as dark and compact as any black hole. Orbits and radiation behave the same. The masquerade is flawless. Only the interior physics betrays the difference. The boldness of this idea was not lost on the scientific community. Some dismissed it as an unnecessary complication, a speculative fantasy when black holes already explain the observations well. Others welcomed it as a daring attempt to avoid infinities and paradoxes, a proposal that science needed precisely because it challenged what seemed most certain. In that sense, the Gravastar was never just about stars. It was about philosophy, about refusing to accept that the universe ends in places where equations break. It was about daring to believe that nature has another trick hidden behind the curtain of collapse. At the heart of the Gravastar lies a paradox made real. Stability created from the clash of two opposing forces. On one side, gravity pulls inward with relentless strength, a cosmic hammer that smashes stars and bends light. On the other side, vacuum energy pushes outward with equal ferocity, an invisible spring built into the very fabric of space-time. The Gravastar exists in the razor-thin balance between these two powers. Collapse halts not because matter resists, but because space-time itself changes the rules of the game. Vacuum energy is one of the strangest concepts in modern physics. To most people, a vacuum is empty, a void with nothing in it. But quantum theory insists that even emptiness seethes with activity. Tiny fluctuations spark into being and vanish again, particles and antiparticles bubbling at scales too small for direct observation. This restless background energy is always there, a hidden hum beneath the silence of space. On cosmic scales, physicists believe it drives the accelerated expansion of the universe. Inside a Gravastar, it becomes the core, a bubble of negative pressure that resists collapse and forces gravity to a standstill. But vacuum energy alone cannot hold the star together. Without a boundary, it would expand endlessly, spilling outward like an unchecked explosion. This is where the exotic shell comes in, the thin skin of matter that defines the Gravastar's structure. Unlike ordinary matter, exotic matter is allowed by theory to break the usual rules. It can have negative pressure or even negative energy density qualities that sound impossible, but emerge in the mathematics of quantum fields. Exotic matter pushes outward instead of pulling inward. curving space-time in directions normal matter cannot. In the Gravastar, this property allows the shell to contain the bubble, locking the repulsive energy inside and stabilizing the entire object. The scale of this shell defies imagination. If a Gravastar were the size of the Sun, its boundary would be no thicker than the breadth of a hair, and yet it would weigh as much as the star itself. All of the object's mass resides in that razor-thin layer, while the interior contributes almost nothing to the weight. It is like a cosmic eggshell, impossibly strong, holding back a pressure that could rip apart space-time itself. To an observer, it would be invisible, darker than any surface, reflecting nothing. But its presence would define everything about the Gravastar, the boundary between reality outside and the strange vacuum within. This balance is delicate. If the shell failed, the bubble could collapse inward and form a true black hole, or it could rupture outward in a catastrophic release of energy. The Gravastar exists on a knife edge, not collapsing, not exploding, but lingering in a state of perfect stalemate. It is an object that embodies contradiction. Hollow yet heavy, fragile yet indestructible, empty at the centre, yet massive at the edge. To understand how extraordinary this is, consider the alternatives. A neutron star packs the mass of the Sun into a sphere only 20 kilometers across. Its matter is crushed so tightly that protons and electrons fuse into neutrons. A black hole goes even further, collapsing without end. The Gravastar stops just short of that ultimate plunge. It is smaller than a neutron star, darker than a black hole, and stranger than both. It is a star that has died, and yet not died, a survivor masquerading as a monster. If such an object exists, it is not only a new category of celestial body, it is a window into physics beyond the horizon of what we know. It suggests that space-time is not merely a stage where events unfold, but an actor with its own hidden transformations. It hints that the universe avoids infinities by rewriting itself, changing state when pushed too far. In this sense, the Gravastar is not just an alternative to black holes, it is a lesson about reality itself, a reminder that the cosmos always finds ways to outwit our imagination. From a distance, a Gravastar is a perfect mimic. Its gravity bends the paths of stars just as a black hole would. Its presence sculpts disks of gas that spiral inward, heating to millions of degrees and glowing in X-rays. Even the jets of particles that blast from the poles of such systems, driven by magnetic fields wrapped around spinning plasma, could emerge in almost the same way whether the central object is a black hole or a Gravastar. To our telescopes, the two are twins, and yet hidden in the details there may be ways to tell them apart. One possibility lies in the light itself. When matter falls toward a black hole, it crosses the event horizon and disappears forever. Radiation from the infallen gas abruptly cuts off at the edge, but a Gravastar has no true horizon. Instead, matter slams into its exotic shell. In theory, this impact could produce subtle differences in the radiation we observe, tiny bursts, echoes, or flickers that black holes would never generate. Detecting such signatures is like trying to hear a whisper in a storm, but with each new telescope, the storm grows quieter. Another clue may come from gravitational waves, the ripples in space-time produced when massive objects collide. In 2015, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, detected the first such waves from the merger of what appeared to be two black holes. Since then, dozens more signals have been captured, each one confirming Einstein's predictions. But theorists have wondered, what if some of those collisions involved Gravastars? The difference would be subtle. A black hole merger produces a final ring-down signal as the new horizon settles. A Gravastar merger, by contrast, might produce echoes, faint ripples bouncing inside the shell before leaking out again. If those echoes are there buried in the noise, they could be the first proof that Gravastars are more than theory. So far, the data has been inconclusive. Some researchers claim to see hints of echoes in the LIGO results. Others argue the signals are statistical illusions, patterns drawn from randomness. The debate is ongoing, fierce and unresolved. But the mere possibility that such evidence could exist keeps the search alive. Each new run of detectors, each upgrade in sensitivity brings us closer to an answer. If even one merger shows the unmistakable fingerprint of a Gravastar, astrophysics will be transformed overnight. Then there is the question of shadows. The Event Horizon Telescope gave us the first direct image of a black hole in the galaxy M87, a glowing ring surrounding a dark silhouette. It was a triumph of both technology and theory, matching predictions almost perfectly. But could a Gravastar produce the same image? Many physicists believe yes, the gravitational lensing, the bending of light around the object would look nearly identical. Yet in the tiniest details, the brightness of the ring, the sharpness of the edge, the distribution of light, there might be discrepancies. As the Event Horizon Telescope sharpens its vision, it may someday resolve whether the dark giants at the centres of galaxies are black holes or cosmic tricksters wearing the same mask. The difficulty is that nature is cruelly clever. Gravastars and black holes are designed by physics itself to be nearly indistinguishable. From across millions of light years, their differences blur into the same shadow. This is why the mystery endures. It is not enough to look. We must listen to the faintest echoes, measure the finest ripples, and imagine possibilities beyond what we can see. Only then might the mask slip, revealing whether the monster we fear is truly there or whether it has always been something stranger. If gravastars exist, they are not merely exotic objects hiding in the shadows of galaxies. They are philosophical revelations, silent statements about how the universe chooses to operate when pushed to its extremes. For black holes demand that we accept a breakdown, a place where equations fail, where infinities appear, where information seems to vanish. Gravastars, by contrast, whisper of balance. They suggest that when nature faces contradiction, it bends but does not shatter. It finds a hidden route around the abyss, preserving its laws in ways we may only barely comprehend. This is why the debate between black holes and gravastars is not only about astronomy, it is about the foundations of reality itself. If singularities truly exist, then our current theories are incomplete, and somewhere beyond lies a deeper physics that must one day replace them. If gravastars exist instead, then perhaps that deeper physics is already visible, encoded in the way vacuum energy and exotic matter cooperate to prevent collapse. In either case, the cosmos is not merely a theatre of stars and galaxies, but a proving ground for the very logic of existence. Think about the information paradox again, not only as a technical puzzle, but as a philosophical dilemma. If black holes destroy information, they violate the principle of determinism, the idea that the future can be traced from the past. They create a hole not just in space-time, but in meaning itself. Gravastars avoid this horror. By allowing information to linger on the shell or within the bubble of vacuum energy, they preserve continuity. They tell us that the universe remembers that nothing is truly erased, no matter how deep the darkness. For a civilization built on memory, cause and effect, this difference is staggering. And yet the gravastar is more than a cosmic safeguard. It is a metaphor for the universe's slyness. Imagine standing before what you believe is a solid wall, only to discover it is a curtain hiding a chamber beyond. For decades we have treated black holes as walls, ultimate barriers at the edge of knowledge. Gravastars invite us to tug at the curtain. They remind us that what looks final may be an illusion, that what seems like the end may instead be a transition to another order of reality. This idea resonates with the history of science itself. Again and again, what once seemed absolute was overturned by deeper understanding. The Earth once appeared flat. The heavens once seemed fixed. Space once seemed empty. Each time nature revealed hidden complexity. Gravastars fit perfectly into this tradition of surprise. They suggest that the monsters of gravity once feared as cosmic devourers may actually be gateways to subtler truths. Of course we must be cautious. The mathematics is elegant, but elegance alone is not proof. Theories are not reality until observation confirms them. But even if gravastars are never found, their role in the scientific imagination is crucial. They remind us to question, to doubt, to resist the comfort of accepted truths. They sharpen our minds against the assumption that we already know the limits of nature. In that sense, gravastars are valuable whether or not they exist. They embody the scientific spirit, bold, defiant, willing to imagine the impossible in order to test the real. And yet if even one gravastar is confirmed, the implications would ripple through every field of physics. It would mean that dark energy is not only the engine of cosmic expansion, but also the heart of collapsed stars. It would mean that exotic matter, long a speculation, truly shapes the structure of reality. It would mean that every so-called black hole could be something else entirely. In a single stroke, our picture of the universe would change not into chaos, but into a more intricate and astonishing order. The death of a star is one of the most violent acts in the universe. For millions, sometimes billions of years, a star lives in delicate balance. Gravity pulls inward, trying to crush its mass, while nuclear fusion pushes outward, releasing energy from the fusion of lighter elements into heavier ones. As long as fusion continues, the star shines steadily, its life a battle of opposites held in perfect equilibrium. But eventually the fuel runs out. Fusion slows, pressure drops, and gravity begins to win. The collapse begins. For smaller stars, the collapse halts early. A star like our Sun will become a white dwarf, its matter compressed but stable, shining faintly for billions of years. For more massive stars, the collapse drives matter into neutron-rich states, producing neutron stars where a spoonful of material weighs billions of tons. But when the star is extremely massive, several times heavier than the Sun, even neutron degeneracy cannot resist gravity. In the standard story, collapse continues without limit until a black hole is born. Yet here at this very threshold is where the Gravastar may emerge. According to the theory, as matter crushes inward and densities skyrocket, conditions may reach a tipping point. Instead of matter compressing into an infinitely dense point, space-time itself may undergo a phase change. Quantum fluctuations normally confined to the smaller scales could swell into dominance. Vacuum energy hidden everywhere in the universe could be trapped inside the collapsing core. Instead of continuing towards singularity, the collapse would stall. The interior would inflate into a bubble of vacuum energy, while a razor-thin shell of exotic matter crystallized around it, locking the structure in place. The star does not vanish into an abyss. It becomes hollow balance, transformed into a Gravastar. This process is almost impossible to picture in human terms, but consider water again. At the right pressure and temperature, water can suddenly shift state, freezing or boiling. The molecules remain the same, but their arrangement and behavior change dramatically. In the Gravastar scenario, space-time itself behaves like that water, shifting into a new phase when pushed beyond a critical point. Collapse does not continue forever. Instead, it transforms, rewriting the fate of the star. One of the most fascinating aspects of this idea is that the formation of Gravastars may not be rare. If the conditions for phase transition exist, then many stars thought to have collapsed into black holes could instead have become Gravastars. From the outside, we cannot yet tell the difference. When astronomers point their instruments at the hearts of galaxies, at binary star systems, or at sources of X-rays, they may already be watching Gravastars at work, masquerading as black holes. Still, the theory faces challenges. The existence of exotic matter remains hypothetical. We know that negative pressure is possible in principle. After all, dark energy seems to behave that way on cosmic scales. But whether it can form in the collapse of a single star is unknown. Could such matter really crystallize into a shell? Could it remain stable for millions or billions of years? These questions remain unanswered. Yet even without proof, the idea is captivating because it offers an escape from the inevitability of singularities. It proposes that nature has built-in safety valves, ways to stop collapse from reaching the impossible. If Gravastars do form, their life cycles would mirror those of black holes. They could exist in binary pairs, spiraling together until they collide. They could sit at the hearts of galaxies, anchoring vast swarms of stars. They could power quasars and jets, feeding on matter just as black holes do. From our perspective, the universe would look the same, but in reality, the structures would be different, their interiors hollow instead of crushed. The thought is both unsettling and exhilarating, that we may have already found Gravastars without realizing it, mistaking them for black holes, simply because we cannot yet see their hidden cores. If Gravastars are real, their influence would reach far beyond the death of individual stars. They could shape the very architecture of galaxies, perhaps even the history of the cosmos itself. For decades, astronomers have known that at the heart of nearly every galaxy lies a dark, massive object, millions or billions of times heavier than the Sun. These giants anchor the swirling disks of stars around them, their gravity binding entire systems together. We have called them supermassive black holes. But if Gravastars exist, could these dark hearts be something else entirely? The idea is tantalizing. A supermassive Gravastar would mimic every feature we attribute to a black hole at a galactic core. It would bend space so severely that orbits near its edge would become dizzying whirls. It would devour gas clouds, sparking quasars that blaze brighter than galaxies. It would sculpt jets of plasma that stretch for thousands of light years, visible across the universe. From every observable angle, it would behave like a black hole, and yet its interior would be hollow, its center, a bubble of vacuum energy, its shell, a razor-thin horizon that preserves rather than destroys information. Entire galaxies might dance around objects that are not monsters at all. but cosmic tricksters hiding in plain sight. The implications of this are staggering. If the cores of galaxies are gravastars, then vacuum energy plays a role not only in the expansion of the universe, but also in the daily mechanics of cosmic life. Dark energy. The mysterious force accelerating the cosmos would not be confined to the void between galaxies. It would dwell inside the very centres of galaxies themselves, bound into shells of exotic matter. The same energy that stretches the universe might also hold stars in orbit, linking the fate of the cosmos to the fate of Gravastars. Consider how this might change our view of galactic evolution. Black holes are thought to regulate star formation, feeding on gas clouds and shaping the growth of galaxies through their outbursts and winds. Gravastars could do the same, but with subtle differences. If their shells reflect or store information, then the dynamics of matter falling in could be altered. Perhaps some fraction of infalling gas rebounds, producing echoes of energy. Perhaps jets from Gravastars differ slightly from those of black holes, carrying signatures we have yet to decode. Over billions of years, such differences might ripple outward, influencing how galaxies form their stars, how they shine and how they die. On a larger scale, Gravastars could be part of the balance that governs the universe itself. Instead of singularities punctuating space-time with impossible infinities, there would be hollow vaults of vacuum energy, each one a reminder that nature resists absolute collapse. The cosmos would not be sprinkled with tears in the fabric of reality, but with structures that preserve it. Strange fortresses built of emptiness. It is a vision both eerie and reassuring. Eerie because it suggests that what we see is a disguise. Reassuring because it tells us that the laws of physics do not end in chaos but in hidden order. If this is true, then our universe is not merely filled with gravastars. It is defined by them. Every galaxy, every cluster, every grand structure in the cosmos could be tied to their presence. We may live in a universe where hollow stars born from collapse but stabilized by exotic forces have been silently guiding the evolution of galaxies since the dawn of time. And we peering through telescopes and detectors may only now be beginning to suspect the trick. The thought that gravastars might hide at the hearts of galaxies leads naturally to an even deeper question. What is their connection to the very fabric of the universe? At their core lies vacuum energy, a mysterious pressure that pushes outward rather than pulling inward. On the larger scales, we know this energy by another name, dark energy, the force that is driving the accelerated expansion of the cosmos. Could it be that gravastars are not only cousins of black holes, but also laboratories of dark energy, miniature mirrors of the universe itself? Dark energy is among the greatest mysteries of science. Observations of distant supernovae in the late 1990s revealed that the universe is not slowing down under the pull of gravity as once thought, but speeding up. Something unseen and unexplained is pushing galaxies apart, stretching space-time at an ever-increasing rate. Today, cosmologists estimate that nearly 70% of the universe is composed of this elusive substance. It is everywhere, woven into the emptiness, silent yet dominant. And in the heart of every gravastar it might be concentrated, bottled, held in a cosmic vault. This possibility is unsettling. If gravastars exist, then every one of them contains a pocket of the same energy that rules the cosmos. Their interiors are not just hollow, they're echoes of the universe's own expansion, bubbles of the same pressure that drives galaxies apart. Imagine the symmetry of it. The vast universe expanding on the outside while countless gravastars carry fragments of that expansion inside. Stars-like galaxies form, and in their darkest corners the very essence of cosmic growth is stored in miniature. If this is true, gravastars could help explain why dark energy behaves the way it does. Perhaps the universe is not a uniform sea of mysterious pressure. Perhaps some of that energy is locked away in collapsed stars released slowly over cosmic time, feeding the balance that governs expansion. In this picture, gravastars would not merely be astronomical curiosities, but essential components of the cosmic machine regulators of growth, keepers of balance between collapse and expansion. And then there is the question of fate. Cosmologists debate how the universe will end. Will it expand forever, thinning into a cold and empty void? Will dark energy grow stronger, tearing galaxies and atoms apart in a final big rip? Or will the expansion slow and reverse, collapsing back into fire? If gravastars are real, their existence may tilt the answer. They could act as reservoirs of energy, slowing or altering the march toward entropy. They could be the seeds of a reborn universe, hollow shells that outlive galaxies carrying within them the memory of creation. The idea is haunting. When we gaze at Gravastars, we may not only be seeing the remnants of dead stars, we may be glimpsing the architecture of the cosmos itself written on both the grandest and the smallest scales. In their hollow cores, the fate of the universe may already be inscribed. In the vast catalogue of cosmic ideas, Gravastars do not stand alone. They belong to a family of strange theoretical objects, each born from the same desire, to escape the contradictions that black holes present. Among these relatives are boson stars, dark energy stars, and even the legendary wormholes. Each offers a glimpse of how the universe might build structures stranger than any fiction, and each in its own way mirrors aspects of the Gravastar while also challenging its uniqueness. Boson stars are perhaps the closest cousins. Instead of being made of protons, neutrons, and electrons, they're imagined to be composed of bosons, particles that follow different quantum rules. Where fermions resist being packed together, bosons can pile into the same state, forming vast quantum condensates. A boson star would be an enormous ball of such particles stabilized not by degeneracy pressure, but by quantum coherence. Like Gravastars, they would be dark, compact, and difficult to detect. They might even masquerade as black holes in certain observations, but unlike Gravastars, they do not require exotic shells or vacuum bubbles. Their strangeness lies in their quantum substance matter, behaving on galactic scales the way light does in lasers. Then there are dark energy stars which sound almost identical to Gravastars at first glance. Both rely on the idea of vacuum energy or negative pressure. Both attempt to sidestep the singularity, and both suggest that what we call black holes may in fact be hollow imposters. The distinction lies in details. Some versions of dark energy stars lack the thin shell that defines Gravastars, while others envision slightly different balances of pressure and gravity. In truth, the line between Gravastar and dark energy star is blurry, more a question of terminology than of principle. Both point to the same unsettling conclusion that what we see as black holes may in fact be cosmic vaults, filled with the same force that drives expansion across the universe. And then there are wormholes, the most exotic of them all. Unlike Gravastars or boson stars, wormholes are not alternative forms of collapsed stars, but tunnels through space-time itself, shortcuts linking distant regions or even different universes. Exotic matter with negative energy density is again the key preventing the throat of a wormhole from collapsing. In this way, Gravastars and wormholes share a family resemblance. Both require strange forms of matter that break our ordinary rules. Both arise from the refusal to accept singularities. Both haunt the boundary between physics and imagination. The difference is that Gravastars are designed to look exactly like black holes, while wormholes, if they exist, would reveal themselves as pathways, perhaps even as engines of travel. By comparing these possibilities, we see the larger pattern. The universe may be far more creative than our textbooks suggest. Black holes may not be the final word, but only one mask among many. Boson stars show us what happens when quantum matter scales up. Dark energy stars remind us that vacuum energy may dominate in ways we have not yet seen. Wormholes suggest that space-time itself may be pliable and network rather than a stage. Gravastars fit perfectly into this gallery, half familiar, half alien, reassuring in appearance but revolutionary in substance. And yet among all these candidates, Gravastars remain uniquely compelling. They explain not only the avoidance of singularities, but also the preservation of information, the echo of dark energy, and the mimicry of black holes. They are tricksters designed to fool our eyes, vaults built of emptiness paradoxes given form. If boson stars are quantum, and wormholes are pathways, then Gravastars are masks. Dark reflections reminding us that even the things we believe we know best may not be what they seem. When astronomers peer into the cosmos, they are confronted with shadows that all look the same. Whether a compact object is a black hole, a Gravastar, a boson star, or something else. Entirely, the signals are deceptively similar. Radiation swirls in hot accretion disks, jets pierce space, and gravity bends light into rings of fire. For the observer, the question is no longer what we see, but what lies beneath the mask. The challenge is subtle, to decode the whispers hidden in the chaos of matter, light, and gravity, to catch the tiny differences that distinguish one dark heart from another. Consider the boson star. Unlike Gravastars, it has no shell, no vacuum bubble. Its interior is a quantum condensate, a single giant wave of bosonic matter. If we could probe it, we might find that infalling particles behave differently, scattering in ways that betray the softness of its core rather than the hardness of a shell. Its gravitational waves might be slightly altered, the final ringing tone of a merger stretched or dampened by the quantum substance within. Yet to our current detectors, the differences blur into noise. What should be a symphony of variations is heard as a single monotonous note. Dark energy stars, on the other hand, sit almost on top of the Gravastar in concept. Both rely on negative pressure. Both suggest that horizons may be illusions. But a Gravastar carries with it the distinctive razor-thin shell, a skin that gives its structure a line between inside and out. Without such a shell, a dark energy star risks diffusing into the cosmos, its boundaries uncertain, its stability questionable. The Gravastar, in contrast, is tightly defined, its form precise, its deception perfect. The observational challenge is immense, to see not only the behaviour of the disk or the bending of light, but the way matter interacts with that invisible shell. And then there are wormholes, the great dreamers of science fiction. They are nothing like Gravastars in appearance, yet their survival also depends on exotic matter. If wormholes exist, they would announce themselves not with shadows but with distortions, sudden shifts in the path of light, strange gravitational signatures that hint at tunnels rather than vaults. Gravastars mimic black holes by design. Wormholes, if ever found, would break the disguise, completely opening doors rather than hiding secrets. In this sense, Gravastars are the tricksters of the family, while wormholes are the rebels. For astronomers, the comparison is not merely academic. Each model carries a different implication for the fate of matter and information. A boson star suggests that quantum fields may dominate cosmic structures. A wormhole suggests that space-time itself is flexible, a fabric to be threaded. A Gravastar suggests that collapse is never final, that the universe avoids infinities by rewriting the rules. Each possibility reshapes the boundaries of physics. Each demands a different future for our understanding of reality. What unites them is a single haunting truth. Our instruments are not yet sharp enough. The cosmos has given us riddles written in the faintest lines, and we read them with blurred vision. But the day will come when detectors reach the needed sensitivity, when gravitational wave observatories can separate echoes from noise, when telescopes can resolve the edges of shadows with exquisite clarity. On that day, one mask will slip. The question is which? Will we find that black holes are true, that singularities really exist, and that nature accepts infinity as part of its design? Or will we find instead that every shadow hides a hollow trickster, a Gravastar preserving the order of the cosmos? Until then, the comparisons remain vital. They remind us that even when two objects appear identical from the outside, their stories can be radically different within. Just as two houses may share the same facade but hide entirely different rooms, so too may the dark giants of the universe conceal truths we have barely begun to imagine. Gravastars, boson stars, dark energy stars, wormholes, all are possibilities, all are disguises. And somewhere out there among the galaxies, one of them is waiting to be unmasked. For all the elegance of theory, Gravastars will remain only speculation, until the universe itself reveals a clue. That is why the search now shifts from equations to instruments, from thought experiments to the raw data of telescopes and detectors. Over the last decade, humanity has built machines capable of sensing the universe in ways that were once unimaginable. They may be the keys that determine whether Gravastars are fantasy or fact. The most dramatic breakthroughs have come from gravitational wave observatories. In 2015, LIGO announced the first detection of ripples in space-time from the collision of two compact objects. The waves that reached Earth carried the memory of that titanic event across more than 1 billion light-years. Since then, LIGO, joined by Virgo in Europe, and now Kagra in Japan, has recorded dozens of similar signals. Most are explained as black hole mergers, but a whisper of doubt remains. If some of those events were Gravastars colliding, the waves should carry subtle differences, echoes in the final ring-down, faint repetitions of the signal as vibrations bounced inside exotic shells before escaping. Some scientists claim to have seen such echoes buried in the data, though the evidence is weak, contested, and debated fiercely. Are they real features of Gravastar physics, or are they artifacts of noisy detectors? The controversy is unresolved. But the mere existence of the debate shows how close we may be to the truth. Every new upgrade to these detectors improves their sensitivity. Within the next decade, the ability to distinguish between a black hole and a gravastar by its gravitational song may finally be within reach. Meanwhile, the Event Horizon Telescope has given us our first direct glimpses of compact objects. In 2019, it delivered the image of the shadow in galaxy M87, and later the silhouette of Sagittarius A star at the centre of the Milky Way. The results matched the predictions for black holes with astonishing precision. But again, gravastars cannot yet be ruled out. Their lensing of light would appear nearly identical. Only in the fine details, the sharpness of the edge, the distribution of brightness around the ring might the difference appear. As the Event Horizon Telescope expands with more stations, sharper imaging, and broader frequencies, it may soon test whether those shadows truly belong to black holes, or whether gravastars have been masquerading before our eyes. Other instruments also join the hunt. Space telescopes scanning X-ray and gamma-ray skies record the fury of matter as it plunges toward invisible objects. If that matter strikes a solid shell instead of vanishing into an event horizon, there could be bursts, reflections, or unusual cut-offs in the radiation. None have been confirmed yet, but the possibility remains open like a ghost signal waiting to be decoded. Future missions may carry the sensitivity to find these fingerprints peeling away the disguise. Together, these efforts form a single tapestry of exploration. Gravitational wave observatories give us the sound of the cosmos. The Event Horizon Telescope gives us its shadow. High-energy satellites give us its sparks of fury. Piece by piece, they bring us closer to unmasking the giants. Whether the answer turns out to be black holes, gravastars, or something stranger still, the quest itself is a triumph proof that human curiosity can stretch across billions of light-years chasing whispers in the dark. If gravastars were ever confirmed, the shock would not be confined to astronomy. It would ripple through the very foundations of physics, forcing us to rewrite the laws that have guided science for over a century. For general relativity, the discovery would be both a vindication and a challenge. On the one hand, gravastars show how Einstein's equations can bend without breaking, how space-time might resist singularities rather than succumb to them. On the other hand, their existence would prove that general relativity, elegant as it is not the whole story. Something deeper must lurk beneath some union with quantum mechanics that allows shells of exotic matter and bubbles of vacuum energy to emerge naturally. For decades, physicists have hunted for this elusive union, the so-called theory of quantum gravity. String theory loop quantum gravity causal sets all of these frameworks attempt to weave the fabric of space-time into the quantum realm, but black holes with their singularities have always been the battlefield where these attempts falter. Gravastars change the terrain. Instead of an infinite point where theory breaks down, they provide a structure where quantum effects manifest on astronomical scales. If they exist, then the path to quantum gravity may not lie only in particle accelerators or abstract mathematics, but also in the skies above us, in the very objects we once misnamed as monsters. The implications stretch further still. If gravastars are real, then vacuum energy is not merely a diffuse background that drives cosmic acceleration. It is an active player able to clump, stabilize, and shape structures in the universe. That raises profound questions about the nature of dark energy. Is it a uniform sea across the cosmos, or can it localize and condense into pockets? If it can, then perhaps gravastars are not just isolated curiosities, but common outcomes of collapse hidden everywhere. We once thought black holes reigned supreme. This reimagining of dark energy ties directly into cosmology, where theories of the multiverse already suggest that vacuum states may vary from one region to another. Gravastars in this sense could be windows into other possible universes, bubbles of different phases trapped within our own. And what of information? If gravastars preserve it, then the paradox that haunted Hawking evaporates. But the solution raises its own mysteries. Where is the information stored in the shell, in vibrations of the vacuum, in quantum correlations smeared across space-time itself? Could it be that the shell of a gravastar functions like a hologram encoding the three-dimensional history of everything it absorbs onto a two-dimensional surface? If so, then gravastars become not only alternatives to black holes, but laboratories for the holographic principle, the idea that the universe itself may be a projection from a deeper layer of reality. The philosophical weight of such discoveries is immense. For centuries, science has progressed by revealing that nature avoids infinities, that what seems impossible is often resolved by hidden order. Atoms do not collapse because of quantum rules. The speed of light is finite because space-time itself sets the limit. Gravastars would fit seamlessly into this pattern, showing us once more that the universe refuses breakdowns, that it bends reality before letting it break. And yet the price of such knowledge is humility. If gravastars exist, then what we thought were the most certain monsters of physics, black holes, are revealed to be illusions. Our greatest triumphs of prediction become disguises, placeholders for a deeper truth. The universe, it seems, never ceases to remind us that certainty is temporary, and that behind every shadow lies another mystery. To speak of gravastars today is to linger at the edge of speculation. But speculation is where tomorrow's science often begins, and it is worth asking. What if we could someday approach one of these hollow stars? What if, against all odds, a civilization could not only detect a gravastar but also learn to tap its secrets? The consequences would be staggering, both wondrous and terrifying. At the heart of every gravastar lies vacuum energy, the same mysterious force that drives the expansion of the universe. If such energy could be extracted or harnessed, it would dwarf every power source humanity has ever known. Even a tiny fragment might contain enough energy to fuel entire civilizations for eons. A gravastar could become the ultimate power plant, a cosmic vault holding the energy of creation itself. Of course, the challenge is monumental. The shell of exotic matter that defines a gravastar would be impenetrable, by ordinary means harder than any known material forged from the strange mathematics of negative pressure. But if a way could be found to couple with it to draw even a whisper of energy across its boundary, the rewards would be limitless. And then there is the possibility of propulsion. Imagine harnessing the vacuum bubble within a gravastar as a drive, a source of repulsive force capable of bending space-time around a vessel. Instead of crawling between stars at a fraction of light speed, ships might surf on waves of engineered vacuum, leaping across interstellar distances in spans of years or even days. In such visions, gravastars are no longer merely cosmic curiosities. They are engines of a future humanity, the very tools that could carry us to other stars. But speculation does not stop at utopia. The same forces that could power civilizations could also destroy them. If a gravastar's shell were destabilized, its vacuum interior might rupture outward in an explosion more powerful than any supernova. The release of energy could sterilize star systems, unbinding planets from their orbits, tearing apart the fragile structures of life. In the wrong hands or through miscalculation, gravastars could become the most destructive weapons the universe has ever known. They would not need to be moved or aimed. Simply triggering their collapse would unleash devastation on a scale beyond imagination. This duality is always present in cosmic speculation. The same stars that light our nights also forge the heavy elements that can annihilate worlds. The same physics that explains the atom can build bombs as easily as it builds power plants. Gravastars, if they exist, would embody this tension perfectly. They're at once sources of unimaginable stability and potential engines of apocalypse. And yet perhaps the most profound gift they could offer is neither energy nor weaponry but knowledge. If humanity ever stood at the edge of a gravastar and survived to study it, the lessons drawn from its shell and its vacuum would change everything. We would learn how space-time itself transforms under pressure. We would glimpse the workings of quantum gravity not as theory but as experiment. In their hollow silence, gravastars may hold the answers to the very questions that have haunted physics for a century. To dream of such encounters is to recognize both our insignificance and our potential. We may never touch a gravastar, we may never unlock its power, but in daring to imagine, we prepare ourselves for discoveries that lie ahead. And in that act of imagination, we echo the very spirit that created science in the first place. The refusal to accept the obvious, the courage to believe that nature always hides another layer beneath the mask. Long before telescopes revealed the true scale of the cosmos, humanity looked to the night sky and saw stories. Stars became gods, constellations became myths, and the dark void between them became a canvas for fear and wonder. Today we peer deeper than ever before, armed with equations and detectors instead of folklore. And yet the mysteries we uncover still resonate like ancient myths. Gravastars, if they exist, may not only transform our science, they may also reshape the symbolism we attach to the stars themselves. For centuries, the death of a star has been imagined as a finality, a blaze of supernova followed by silence. Black holes turned that silence into terror. Endless collapse, infinite density, an abyss from which nothing escapes. They became symbols of annihilation, metaphors for despair and inevitability. Gravastars, in contrast, embody a different image. They are not pits of destruction, but vaults of preservation. They suggest that even at the edge of collapse, the universe chooses balance over ruin. In them, death becomes transformation rather than erasure, a hollow survival rather than a void. Such a vision carries profound philosophical weight. It speaks to the human condition, to our fear of endings and our hope for continuity. Gravastars tell us that nature resists the final full stop, that the script of reality avoids abrupt conclusions. They remind us that behind the appearance of absolute darkness, there may be hidden order, that what seems like extinction might instead be conservation in disguise. In this way, they mirror our deepest cultural myths. Phoenixes rising from ashes, seeds lying dormant through winter, only to bloom again in spring. Culturally, they may also shift how we perceive our place in the cosmos. If black holes are monsters, then we live in a hostile universe where even the laws of physics turn against us. If gravastars are real, then the universe is trickster-like deceptive but ultimately protective, refusing infinities and preserving information. That view is no less awe-inspiring, but it carries a different emotional resonance. It paints the cosmos as a place of hidden structure, not chaos, a reality that is cunning, but not cruel. Artists and storytellers may someday seize on this imagery. A gravastar could become a metaphor for resilience, for the idea that hollowness is not emptiness but potential. In literature, it might symbolize the masks we wear, the hidden cause within us that outsiders cannot see. In philosophy, it might stand for the refusal to accept paradox as final, the belief that even the greatest contradictions conceal new truths. In religion, it could echo the promise of continuity beyond death, a cosmic version of spirit persisting where matter fails. And for science itself, the symbolism is equally powerful. Gravastars remind physicists not to settle, not to accept infinities as answers, not to confuse the limit of theory with the limit of reality. They embody the very spirit of discovery, the insistence that the universe is always one step ahead of our imagination. In that sense, they're both a physical hypothesis and a cultural mirror reflecting our need to find meaning in the stars. Whether or not gravastars exist, their story has already begun to shape the way we think about the cosmos. They are reminders that science and myth are not opposites, but partners. Where myth gives us images to hold, science gives us equations to test. Both speak to the same hunger, to see beyond the mask of reality, to glimpse the hidden truth beneath. The discovery of gravastars would not be the end of a mystery. It would be the beginning of an entirely new era. Astronomers, physicists, and philosophers alike would be forced to redraw the map of reality. The questions we have been asking for a century about black holes, about singularities, about the nature of space and time would suddenly shift. A new generation of scientists would rise with new tools, new missions, and new visions of what the universe truly is. In astronomy, the first priority would be to survey the skies once again. Every so-called black hole would have to be reconsidered. Are the shadows at the centres of galaxies truly the event horizons we believed? Or are they hollow stars masquerading as them? Are the mergers detected by LIGO and Virgo really the death dances of black holes? Or are they the collisions of shells of exotic matter echoing across space-time? Entire catalogues would need to be rewritten. Entire models recalibrated. For the first time, we would no longer assume what hides in the dark. We would ask object by object, shadow by shadow. What are you really? In theoretical physics, the consequences would be just as profound. Gravastars would provide a natural testbed for unifying general relativity and quantum mechanics. The exotic matter shell, the vacuum bubble, the balance of pressures, these features would demand explanations that go beyond Einstein, beyond quantum field theory. Researchers would find themselves drawn into new equations, seeking the mechanism by which vacuum energy crystallizes the rules that allow exotic matter to stabilize. In solving these puzzles, they might also uncover insights into dark energy itself, perhaps even into the fate of the cosmos. Gravastars would become the laboratories of ultimate physics, the places where the deepest laws of nature reveal themselves. But the changes would not stop at science. Our culture, our storytelling, even our philosophy would shift. The language of black holes, annihilation, singularity, abyss has seeped into literature, art, and the way we describe despair. Replace those images with Gravastars and new metaphors would bloom. We would speak of hidden cores, of preserved information, of hollowness that is not emptiness but potential. The cosmos would no longer be a graveyard filled with monsters, but a stage filled with masks and secrets, each shadow a possible vault of memory. Future generations might even grow up with different myths of the stars. Instead of fearing the black maw at the centre of galaxies, they might wonder at the trickster vaults that hold the very laws of nature within. Students in classrooms might learn not only that the universe expands, but that its expansion is echoed in miniature inside Gravastars. Poets might speak of the shells of stars as symbols of resilience of the cosmos refusing to collapse into nothingness. In every corner of human thought, the idea of Gravastars would leave its mark. Perhaps the greatest change of all would be psychological. For centuries, black holes have stood as the ultimate reminder of limits. Places where light dies, where information ends, where knowledge itself is swallowed. Gravastars turn that story on its head. They say, even at the brink of collapse, the universe preserves, remembers, resists. That message would reshape how we think of our own existence. We too live at the edge of mysteries, staring into shadows we cannot yet explain. And like the Gravastar, perhaps we too carry hidden strength, a hollow that is not nothing but possibility waiting to be revealed. When we speak of Gravastars, we are not only asking about the fate of collapsing stars, we are also in a subtle way asking about the fate of the universe itself. For Gravastars embody balance, the refusal of space-time to collapse into singularity, the preservation of order when chaos seems inevitable. And if such balance exists on the scale of stars, what might it mean for the cosmos as a whole? Could Gravastars hint at how the universe itself will die, or how it might escape death altogether? Cosmologists today entertain several scenarios for the universe's end. In one known as the heat-death expansion continues forever. Galaxies drift apart, stars burn out, and all that remains is a thin sea of particles colder and dimmer with every passing trillion years. In another, called the Big Rip, dark energy grows stronger, until not only galaxies but stars, planets, and even atoms themselves are torn apart by its relentless pull. A third possibility is the Big Crunch, where expansion slows and reverses, collapsing the universe back into a fireball. Each scenario feels final, absolute, and grim, yet Gravastars offer a different perspective. Inside each Gravastar is a bubble of vacuum energy, a miniature reflection of the dark energy that drives cosmic expansion. If these objects are common, then the universe is not only expanding outward, but also storing fragments of that expansion inward, locking away pieces of dark energy inside its hollow stars. Perhaps this reservoir plays a role in balancing the cosmos. Perhaps Gravastars are the universe's way of conserving, redistributing, or even recycling the very energy that dictates its fate. If so, the end of the universe might not be absolute. It might be another transformation, a phase change on the grandest scale, just as Gravastars are phase changes on the stellar scale. Imagine then a far future when the last stars have burned out. The universe is dark, but Gravastars remain silent and hollow, carrying bubbles of vacuum energy within. Could these bubbles grow, merge, or ignite in ways we cannot yet imagine? Could they become seeds for new universes, each Gravastar a womb of creation waiting to burst? Some theorists whisper of such possibilities that black holes, or Gravastars if they exist, may be cradles for new universes, buds sprouting from the trunk of cosmic history. If true, then death itself is an illusion, and the universe is a self-renewing tree growing new branches when old ones wither. Even if such speculation proves false, Gravastars still alter the way we confront cosmic endings. They tell us that singularities are not inevitable, that infinities can be avoided, that breakdown is not the final word. They whisper that even when collapse seems absolute, nature may hide a trick, a hollow core that preserves memory and structure. To imagine the universe filled with such objects is to imagine a cosmos that resists erasure, one that finds continuity even in death. For us tiny creatures staring at the stars, this vision matters. It tells us that despair is not the only lens through which to view the future. Even the universe, vast and indifferent, may carry within it structures that resist finality. Gravastars become symbols not just of stellar death, but of cosmic resilience, reminders that the story of time may not end in silence, but in transformation. The allure of Gravastars is undeniable, but in the halls of science, allure is never enough. The community of physicists has greeted the idea with fascination but also with sharp skepticism. For every paper exploring the elegance of the model, there are others that question its plausibility, pointing to gaps, weaknesses, and the stubborn fact that black holes already explain the data remarkably well. If Gravastars are to be accepted, they must survive these critiques, and the critiques are formidable. One of the strongest objections concerns exotic matter. The shell of a Gravastar requires material with negative pressure or negative energy density properties that ordinary matter cannot provide. While quantum theory allows for such conditions in principle, the Casimir effect, for example, creates small regions of negative energy. Scaling them up to astrophysical levels may be impossible. Critics argue that there is no known mechanism by which the collapse of a star could generate or stabilize such exotic matter. Without it, the Gravastar cannot exist. Another objection points to the elegance of black holes themselves. General relativity predicts them naturally without requiring new ingredients. The mathematics is straightforward. Given enough mass and density, collapse proceeds to an event horizon and singularity. Black holes not only fit the equations but also match decades of observations from stellar orbits to gravitational waves to shadow images. To introduce Gravastar skeptics, say, is to complicate a picture that is already working beautifully. Why multiply entities without necessity? Why trade the certainty of a well-tested model for the speculation of a hollow one? There is also the issue of stability. Even if a Gravastar could form, could it last? The balance between vacuum energy pushing outward and exotic matter pulling inward is delicate. Small disturbances could disrupt it, causing the shell to rupture or collapse into a black hole. Without clear evidence that such structures could remain stable for billions of years, critics see Gravastars as fragile fantasies, unlikely to survive in the violent cosmos. Finally, there is the practical matter of evidence. Observations of black holes have accumulated to overwhelming levels. We have measured the motions of stars whipping around Sagittarius A star with exquisite precision. We have seen gravitational waves from mergers that fit predictions of black holes almost perfectly. We have imaged shadows that align with theory to within a few percent. Gravastars could in principle mimic all of these signatures, but the burden of proof lies with the new idea. Until Gravastars produce a unique testable prediction, some signal that black holes cannot explain, they remain in the eyes of many scientists speculative shadows of a more solid truth. Yet even within these critiques lies the vitality of science. Skepticism is not dismissal, but challenger demand for rigor, clarity, and evidence. Gravastars must earn their place not by replacing black holes outright, but by offering insights black holes cannot. If they succeed, they will reshape physics. If they fail, they will still have served as valuable tools pushing us to test the limits of our understanding. Either way, the debate sharpens our vision. It forces us to look harder at the shadows, to listen more closely to the whispers of the universe. The debate over Gravastars may ultimately be decided not in lecture halls or equations, but in the skies. The next generation of observatories promises to probe the universe with a sensitivity far beyond what we have today. Each new instrument is another set of eyes and ears capable of picking up the faintest signatures that might reveal whether the shadows we see are truly black holes or something stranger hiding in plain sight. Among the most anticipated projects is the Laser Interferometer Space Antenna, or LISA. Unlike ground-based detectors such as LIGO and Virgo, LISA will float in space, its arms millions of kilometers long, free from seismic noise and atmospheric interference. This will allow it to detect lower frequency gravitational waves, the slow, massive mergers of supermassive objects at the centers of galaxies. If Gravastars exist in those places, their collisions might produce echoes or deviations in the waveform that LISA could record with exquisite precision. For the first time, we may be able to hear not only the thundering crash of the merger, but the subtle resonances that follow the possible heartbeat of exotic shells vibrating in space-time. Meanwhile, improvements to ground-based detectors continue. The next upgrades to LIGO and Virgo, along with the development of third-generation observatories like the Einstein Telescope in Europe and Cosmic Explorer in the United States, promise to increase sensitivity by an order of magnitude. These instruments will not only detect more events, but also measure them with finer detail, offering a better chance of distinguishing between the clean ring-down of a black hole and the layered echoes of a Gravastar. If such echoes exist, the instruments of the 2030s may finally make them unambiguous. In parallel, the Event Horizon Telescope is expanding its reach. With more stations around the globe and new capabilities at higher frequencies, it will sharpen the resolution of the shadows it observes. Already the images of M87 and Sagittarius A* matched predictions with surprising accuracy. But Gravastars may hide in the subtleties. The brightness asymmetries, the thickness of the photon ring, the temporal variations in the glow. With each improvement, the possibility grows that we will see a discrepancy however slight that cannot be explained by black holes alone. Such a moment would be revolutionary. Other space-based observatories will contribute as well. X-ray telescopes like Athena planned for the next decade will study accretion disks with unprecedented clarity. Gamma-ray detectors may capture bursts of energy that betray impacts against Gravastar shells. Even neutrino observatories sensitive to the ghostly particles that stream from the most violent cosmic events could provide hints of differences between black holes and their hollow counterparts. Together, these instruments form a coordinated assault on the mystery, each one adding a layer of data, each one narrowing the space where Gravastars can hide. The future, then, is one of promise. For the first time in history, we stand on the threshold of being able to test whether our cosmic monsters are truly what we think they are. In the next 20 to 30 years, the combination of gravitational wave astronomy, horizon imaging, and high-energy surveys may finally provide the smoking gun. If Gravastars exist, they will leave footprints, and if they do not, the shadows will confirm the reign of black holes with even greater certainty. Either outcome will deepen our understanding of reality. What if the skeptics are right? What if Gravastars are nothing more than elegant speculation, mathematical curiosities without physical reality? Then the universe is even harsher than the Gravastar dream suggests. We must accept black holes as they are. Singularities wrapped in horizons, abysses where space-time itself breaks down. In that case, we confront not the trickster vaults of hollow stars, but the brutal finality of collapse with no escape. This path brings us back to the information paradox. If black holes are real and complete, then information, the quantum imprint of every particle that falls in, is lost forever. Hawking radiation leaks energy, but it carries no memory of what was destroyed. In the black hole cosmos, the past is not merely hidden, it is erased. That erasure shatters one of the most cherished principles of physics. Determinism, the idea that the present and future follow logically from the past. Without determinism, the laws of physics cease to be laws. They become approximations fragile and incomplete. Physicists have struggled for decades to avoid this conclusion. Some argue that information must be encoded in the subtle correlations of Hawking radiation, though the mechanism remains unclear. Others propose that the horizon is not smooth at all, but a firewall, a searing boundary that burns information into radiation before it enters. Each attempt, however, comes with contradictions of its own. The debate is fierce, unresolved, and unsettling. If Gravastars do not exist, the paradox remains unsolved at the very heart of physics. For cosmology, the consequences are equally stark. Singularities are not only endpoints of stars, but potential seeds of the universe itself. If black holes truly harbour infinities, then perhaps the Big Bang was one such singularity, a place where all equations failed. This view paints reality as something born from breakdown, a cosmos that emerges not from order, but from mathematical collapse. It is a vision both humbling and disturbing, that the very origin of time is rooted in the same infinities that haunt black holes. Culturally too, the black hole-only universe carries weight. Black holes have become symbols of inevitability, of annihilation, of the futility of resistance. If they are the sole truth, then the cosmos is darker, less forgiving. The shadows at the centres of galaxies are not masks, but maws devouring not only matter, but meaning itself. Humanity must accept that the universe is not obliged to preserve information that memory can truly be destroyed. Yet even this darker vision holds value. It forces us to confront the limits of knowledge. It demands humility in the face of nature's cruelty. It reminds us that not all mysteries will yield to our desire for order. If Gravastars never reveal themselves, then black holes will stand as monuments to the raw power of gravity, teaching us that the universe is not designed for our comfort, but for its own unfathomable logic. Perhaps that is the final irony. Whether Gravastars exist or not, we are left with mystery, Either we face the trickster hollows of exotic matter or the merciless singularities of black holes. In both cases, the lesson is the same. The universe is stranger than we imagined, and the shadows we see in the night sky are never what they first appear. If Gravastars are more than theory, they may hold the power to reconcile the deepest conflicts in modern physics. For over a century, two towering frameworks have guided our understanding of reality. Quantum mechanics, which governs the subatomic world with precision and probability, and general relativity, which governs the cosmos with elegance and inevitability. Both are triumphs. Both are experimentally verified to extraordinary accuracy. Yet when placed side by side, they clash. Black holes with their singularities are where the clash becomes unavoidable. Gravastars in their strange hollowness may provide the missing middle ground. Quantum mechanics insists that information cannot be destroyed. Relativity, when pushed to black hole collapse, seems to say otherwise. The paradox is sharp, unforgiving. But in a Gravastar, the contradiction dissolves. No singularity forms. No true horizon hides information. Instead, the thin shell and the vacuum within act as a storehouse, preserving the quantum memory of everything that falls inside. In this way, Gravastars uphold both principles at once. The smooth space-time of relativity and the indestructible information of quantum theory. This reconciliation resonates strongly with the holographic principle, an idea born from string theory, and later developed in the framework of quantum gravity. The principle suggests that everything within a volume of space can be described by information encoded on its boundary, like a three-dimensional world projected from a two-dimensional surface. Black holes were once thought to exemplify this, with their horizons acting as cosmic hard drives, but Gravastars may embody it even more cleanly. Their shells are literal boundary surfaces on which the history of infalling matter could be written, preserved, and perhaps even read. If this interpretation proves correct, Gravastars would not just be astrophysical objects, they would be living laboratories of the holographic universe. String theory too may find new footing in Gravastars. The exotic matter shells they require align naturally with the kinds of fields and negative energies predicted by string models. Vacuum bubbles echo the multiple possible states of the vacuum in string landscapes, where universes may differ only by the way energy is arranged. Gravastars, if detected, could offer a tangible example of such abstract possibilities, grounding the wild terrain of string theory in observable astrophysical reality. Even loop quantum gravity, a competing approach, might find its reflection in Gravastars. That theory suggests that space-time is not continuous but granular, built from loops and networks at the smallest scales. Singularities in this picture are avoided because space itself cannot shrink indefinitely. The Gravastar, with its finite shell and hollow interior, echoes this idea. It stands as a macroscopic reminder that infinities are illusions, that the universe prefers discrete structures over endless collapse. Thus, a Gravastar serves as bridges. They allow rival theories to project themselves into the stars to see their principles reflected in cosmic mirrors. They are not proofs, not yet, but they are possibilities that give physicists hope that the war between relativity and quantum mechanics can end in truce. And beyond truce, perhaps even in synthesis. If Gravastars exist, they suggest that the universe itself is holographic, string-like loop structured all at once. They would be the signs that no single theory holds the whole truth, but that each has glimpsed a fragment of the greater order. Gravastars would be the puzzle pieces that show us how the fragments fit together. When we think of stars, galaxies, and clusters, we tend to imagine them as the largest building blocks of the universe. But what if Gravastars are something deeper? The true structural units of cosmic architecture, not merely endpoints of stellar collapse, but repeating motifs in the grand design of reality. In this view, Gravastars become less like accidents of gravity, and more like fundamental cells scattered through space-time to regulate balance and preserve the universe's integrity. Each Gravastar is a hollow vault of vacuum energy stabilized by an impossibly thin shell. On its own, one seems exotic, unlikely, almost too strange to believe. But consider billions of them. Consider a cosmos where every supermassive object at a galactic core is not a black hole but a Gravastar. Suddenly these vaults are everywhere, anchoring galaxies, shaping jets, fueling quasars. They are not rare curiosities. They are the hidden skeleton of the universe. In this picture, Gravastars serve a role analogous to biological cells. Just as cells regulate metabolism, store information, and maintain balance within an organism, Gravastars could regulate the flow of energy, preserve the memory of matter, and maintain balance within the cosmos. Their shells are membranes, their interiors reservoirs, their presence essential to the health of the larger whole. Without them, collapse would run unchecked. Singularities would tear the fabric of space-time and the universe would erode into incoherence. With them, the structure is sustained, ordered, and resilient. This metaphor gains strength when we consider the role of vacuum energy. Dark energy pervades the cosmos, driving expansion on the larger scales. If gravastars are concentrations of that same force, then they may act as nodes in a cosmic network distributing and balancing the energy that governs the fate of everything. Each gravastar could be a storage unit, a regulator, a stabilizer in the cosmic machine. Together they form a hidden infrastructure, one that makes the universe not only possible but sustainable. From this perspective, gravastars blur the line between astrophysics and philosophy. They suggest that the universe has mechanisms of self-regulation, that it avoids extremes not by chance but by design. They invite us to imagine the cosmos as a living system, one that protects itself from breakdowns the way organisms protect themselves from disease. In such a cosmos, gravastars are not monsters or anomalies but guardians, silent, invisible custodians of order. If this is true, then our search for gravastars is not merely an astronomical quest. It is a quest to uncover the architecture of existence itself. Each detection would be a glimpse into the hidden scaffolding of the universe, the framework that allows galaxies to form, stars to shine, and life to emerge. Gravastars would cease to be theoretical curiosities. They would become the very grammar of reality the punctuation marks in the story of the cosmos, the quiet signatures of a universe that refuses chaos. The hollow interior of a gravastar invites a question almost too audacious to ask. What truly is inside? We call it a bubble of vacuum energy, a region where space-time has shifted into another phase. But could that phase itself be more than emptiness? Could the void at the heart of a gravastar be the seed of another cosmos, a pocket universe budding from the trunk of our own? Cosmologists have long speculated that our universe may not be unique. The theory of eternal inflation suggests that regions of space-time undergo endless expansion, spawning bubble universes with different properties. Each bubble could carry its own physics, its own constants, even its own dimensions. To us they are unreachable, separated by vast inflating walls. Yet gravastars resemble these bubbles in miniature. Their interiors are inflating regions bound by thin shells. In other words, each gravastar could be a microcosm of cosmic creation, a self-contained fragment of expansion hidden within the husk of a dead star. Imagine this possibility. A massive star collapses, but instead of ending in a singularity, its core blossoms into a new universe. From the outside, we see only a dark shadow, a hollow star that bends light and swallows matter. But from the inside, an entire cosmos may be growing its own galaxies, forming its own stars, shining its own arrow of time, flowing forward. To us, the gravastar is an endpoint. To that interior, it is a beginning. This idea is speculative, yes, but it echoes theories already entertained by serious physicists. Some suggest that black holes themselves could be cradles of new universes, with each singularity acting as a cosmic womb. Gravastars may make this concept more palatable since they avoid the infinities of singularities altogether. Their vacuum interiors resemble the conditions of the early Big Bang. High energy, rapid expansion structure waiting to form, they are like frozen embryos of universes locked within shells of exotic matter. If so, the cosmos we inhabit may itself have been born from such a process. Our own Big Bang could have been the interior of a gravastar in another universe, a hollow star whose shell is now beyond our perception. We are in that sense children of a hidden star living inside a bubble that once belonged to a greater whole. Gravastars then are not only cosmic tricksters but also bridges between worlds, links in an infinite chain of creation. The implications are staggering. Every gravastar could be a potential universe, every galaxy harbouring countless hidden births. Reality would no longer be a single cosmos, but a multiverse of hollow stars, each one nurturing a new domain beyond our reach. The night sky filled with shadows we call black holes would in fact be filled with windows, not openings we can pass through, but hints of other worlds forever sealed from us, yet undeniably real. And for humanity, this vision carries a strange comfort. It suggests that death is never absolute, that even the collapse of a star may spark creation beyond our sight. Just as Gravastars preserve information, perhaps they also preserve possibility. They whisper that the end of one story is the beginning of another, and that our universe itself may be part of an endless lineage of hollow stars giving birth to worlds. If black holes are symbols of forgetting, Gravastars may be symbols of memory. Where black holes erase, Gravastars preserve. Where black holes end stories, Gravastars keep them on record, even if locked beyond our reach. In this sense, Gravastars can be imagined as cosmic librarians, curators of everything that has ever fallen into their grasp. They do not devour information into nothingness, but tuck it away within their shells like secret books written in the strange script of exotic matter. This reframing changes everything about how we see the universe. For centuries, human culture has been haunted by the idea of oblivion, that death is final, that time erases all. Black holes seem to embody that dread on a cosmic scale. Here are places where even light cannot escape, where the very record of existence is deleted. Gravastars offer a gentler vision. They whisper that the universe does not forget that even at the brink of collapse, memory endures. Every photon, every atom, every trace of matter and energy that crosses their boundaries might still exist in encoded form, preserved against the annihilation of time. The philosophical resonance of this is immense. If Gravastars are real, then the cosmos itself is an archive. Reality does not merely move forward, consuming its past, it also remembers. Perhaps the memories cannot be accessed by us, just as the past in our own lives cannot be relived. But the knowledge that nothing is truly lost reshapes how we think of existence. In Gravastars, the universe becomes both actor and historian, both creator and recorder. For science, this idea intertwines beautifully with the holographic principle. The notion that a shell could encode the entire history of what falls in is no longer an abstraction. It is a physical possibility. Gravastars, by their very design, provide the surface where such information could be written. They are nature's own hard drives, formed not by human engineering, but by the laws of physics at their most extreme. If black holes force us to fear the loss of data, Gravastars tempt us with the thought that no data is ever truly gone. Culturally too, the metaphor is rich. Gravastars would become symbols of resilience, of hidden continuity, of the idea that behind silence lies memory. Artists might imagine them as vaults of forgotten stories, philosophers as guardians of meaning, poets as keepers of cosmic truth. They could even alter our relationship with mortality. If stars themselves refuse to let go of what they have consumed, perhaps the universe as a whole preserves echoes of every life, every event, every fleeting spark of consciousness. Gravastars transform the abyss into an archive, and in a more personal sense they mirror our deepest desires. We long to be remembered, to leave a mark, to resist oblivion. Gravastars suggest that the cosmos itself shares that impulse, that memory is woven into its fabric. Perhaps we will never unlock their shells or decode their libraries, but the very possibility that memory endures gives the universe a new character. Less a graveyard of collapsed stars, more a cathedral of preserved stories. If Gravastars are vaults of memory, then they do not merely solve old paradoxes, they create new ones. For what happens when information is never destroyed? Where does it go? How is it stored, and could it ever be released again? These questions turn Gravastars from comforting archives into potential sources of mystery, as profound as the black holes they replace. Consider the scale of what might be preserved. Over cosmic time, Gravastars could accumulate vast quantities of matter and radiation. Each particle carries quantum information. Each infalling wave of light encodes a pattern. If all of it is captured on the shell, then a Gravastar becomes a library of unimaginable size. But can such a library be infinite? The surface area of the shell is finite. At some point, wouldn't it overflow? Or would the physics of exotic matter allow information to compress indefinitely, written in a code beyond our imagination? This question echoes the so-called holographic bound, which suggests that the maximum information content of any region of space is proportional, not to its volume, but to its surface area. Gravastars fit neatly into this rule, their shells serving as natural surfaces where information is written. Yet the thought remains troubling. If their surfaces are saturated, what happens then? Do they reject new information, reflect it, or transform it into radiation? Could this process lead to the tiny bursts or echoes that some claim to see in gravitational wave data? If so, the paradox of information storage might leave fingerprints in the cosmos. Another question arises from the possibility of leakage. If Gravastars preserve everything, are they entirely sealed? Or could information seep out over time encoded in subtle emissions or vibrations? If so, Gravastars might not only store the past, but occasionally reveal it like cosmic storytellers, whispering fragments of what they have swallowed. Detecting such leaks would revolutionize science. Imagine reading the fossil record of a galaxy written not in stone but in the strange radiation of a Gravastar, each pulse a fragment of a forgotten past. And then there is the question of conflict. If Gravastars are also seeds of new universes, then each preserved archive may someday expand outward, reborn as a cosmos of its own. What happens to the information then? Does it survive into the new universe, shaping its laws and structures? Or is it erased in the transition despite all the preservation beforehand? The paradox deepens. Gravastars promise continuity, but at the edge of creation, continuity may fracture again. These puzzles remind us that solving one mystery rarely ends the story. It only opens new chapters. Gravastars protect us from the infinities of singularities, but in doing so, they confront us with other infinities. Infinite memory, infinite possibility, infinite chains of creation. They do not end paradox, they multiply it, shifting it into new forms. And perhaps that is the universe's way. Mystery is never eliminated. It is only transformed, passed along like a torch from one generation of questions to the next. Across centuries, humanity has turned the night sky into a mirror for its hopes and fears. If Gravastars enter our confirmed vocabulary, they will not remain confined to journals and conferences. They will spill into novels, cinema, painting, music, and design, altering the symbols with which we dream. Black holes gave storytellers a language of hunger and annihilation. Gravastars would add a new dialect, masks and vaults hollowness as potential darkness that preserves instead of devours. Science fiction will be the first frontier. Imagine a generation of writers who no longer treat the event horizon as a one-way death, but as a membrane, a living surface that records every trespass. A rescue plot might hinge on decoding patterns from a Gravastar's shell. A heist narrative on smuggling information in through tuned pulses of radiation. A first contact tale on meeting a civilization that learned to read the shells as libraries of the cosmos. Engineers in those stories would speak of phonons humming through the shell of surface modes that can be tickled like a drumhead to store and retrieve messages of antennas built to ride the fine line between reflection and absorption. Cinematic language will also change. Directors love silhouettes. Rings of fire orbits on the brink time stretched into syrup. With Gravastars, the visual grammar expands. You can stage a sequence where an accretion disk trembles, not because it vanishes into a horizon, but because it is striking an invisible shell. You can cut from the silent exterior to an imagined interior, a cold, luminous void that looks like the early universe. The soundtrack can bloom with faint echoes after a merger, a musical motif that returns like a memory refusing to fade. Artists will harvest the metaphor of the shell. Architecture may borrow it as a principle. Buildings that look monolithic from afar yet hide open courts of light within city spaces organized around deliberate hollows. Fashion might echo it with garments that appear opaque but reveal translucent interiors. Under a certain angle, a choreography of concealment and revelation. Even product design could follow. Devices that keep their most vital components at the boundary skins that are function surfaces that think. Poetry and philosophy will embrace the vocabulary of preserved memory. The Gravastar becomes a figure for grief that does not consume for history, that is held for identities that present a mask while protecting a core. Think of elegies that speak of shells that remember the departed, or manifestos that demand institutions. Behave like Gravastars, transparent about power, yet responsible for retaining the record of what they absorb. The rhetoric of the abyss will soften into the rhetoric of the archive. Religions and spiritual traditions may also find resonance. Some theologies already speak of a book of life, a ledger that keeps all deeds. Gravastars provide a cosmic analogue. Not a moral judge, but a physical process that refuses oblivion. Pilgrimages to radio telescopes and sky parks could join existing rituals. Moments where communities listen for echoes from mergers, light years away, hearing in those tremors a liturgy of continuity. The sacred is not destroyed by science. It receives new imagery. Education will change at the level of metaphor. Children learn through pictures, atoms as tiny solar systems, molecules as balls and sticks, space-time as a trampoline. Add Gravastars to that gallery. A dark sphere whose strength sits entirely in its skin, a balloon of vacuum that refuses collapse. Explain conservation of information by tracing ripples along a drumhead instead of watching them vanish into a pit. Show that nature's trick is not cruelty but cleverness. There will be misuses and myths too. Pseudoscience will promise miracle therapies and memory harvesting devices inspired by Gravastar shells. Conspiracy culture will recast every blackout as a secret siphoning of vacuum energy. Our task will be to keep the line bright between wonder and wishful thinking, to defend the difference between metaphor and mechanism. The lesson of Gravastars must remain rigorous even as it travels, and travel it will. Museums will stage rooms where speakers play recorded ring-downs, letting visitors feel gravitational music through their bones. Planetariums will render interiors as minimalist cathedrals of light, teaching humility without horror. Game designers will build levels on the knife edge of stability, where a player must tune pressures on a shell to keep a city-sized Gravastar from collapsing or exploding. The mechanic will teach what the lecture cannot. Balance at the brink. Why does any of this matter? Because the images with which a culture dreams steer the questions it dares to ask. Black hole culture trained us to contemplate limits, endings, irrecoverable loss. Gravastar culture will train us to contemplate stewardship of data, of ecosystems, of memory. It will make what if the mask is the meaning a respectable question. It will normalize the idea that boundaries are not just barriers, but instruments that surfaces can carry thought. In the end, science does not only discover facts, it furnishes civilization with metaphors. If Gravastars become real, they will give us one of the great metaphors of the age, that the universe keeps faith with itself, that even in ultimate darkness something watches over the story. We will still have monsters, we will still have risk, but we will also have a new emblem to set against despair, the hollow star that does not forget. On a clear night in a decade not far from now, the instruments are ready. The ground array is quiet after its latest upgrade. The space antennae drift in formation laser links shimmering across millions of kilometers. In control rooms around the world, scientists watch streams of numbers scroll like rain. What they wait for is not loud. It is a pattern, a shape in the noise, a voice from a collision billions of light years away. First comes the familiar rise and fall, the inspiral song of two compact objects drawing together. The frequency climbs, the amplitude swells, a cosmic chord stretched tighter and tighter until it breaks in a final crash. Every analyst knows this score by heart. It is the music of black holes. But tonight there is something else. After the ring-down fades to near silence, a faint tremor returns. Not once, not noise, a measured echo, then another softer still. A sequence spaced just as a hollow shell would demand the intervals, mapping an interior that refuses to swallow its vibrations whole. Across continents, no one cheers. No one declares victory. The first rule is caution. Teams split the data blind, their fits scramble. The timestamps swap pipelines, invent adversarial tests. They cross-check with electromagnetic observations. A flicker in X-rays where the disk brushes an invisible boundary. A whisper in radio frequencies that arrives late, as if light itself bounced on something hard before escaping. The pattern survives every attack. The echo spacing matches a model that has lived a long time at the edge of plausibility. The quiet in the rooms deepens. Adults who have devoted whole careers to skepticism realize they are running out of ways to say no. Still, the culture of doubt holds. Papers multiply, rebuttals follow. The community rehearses every objection about noise, bias, selection effects, and human hope. Yet each new detection that's seasoned shows the same soft punctuation. After the ring down, a signature as consistent as a fingerprint. The Event Horizon telescope contributes a side glance, a slight skew in the brightness of a photon ring that theory predicted for a surface very near but not quite at a horizon. The case is not absolute. Science rarely grants absolutes. But the balance tilts. The mask begins to slip. Imagine hearing that news as an ordinary watcher of the night. You step outside. The city is quieter than usual, as if it too is holding its breath. Above you hangs the thin curve of the moon and the scatter of stars that still survive the glare. Somewhere out there, two dark giants collided and their music told us the interior was not an abyss. Somewhere a shell rang like a bell no human hand could strike. the feeling that rises is not triumph, it is recognition. We suspected the universe might refuse a final breakdown. Tonight it did not contradict us. What changes first is language. In classrooms the diagram of a black hole remains, but beside it appears a second drawing. Nearly identical except for a wafer-thin sheath at the edge and a hollow core. Teachers explain that nature offered two costumes for the same silhouette, and that we finally learned to tell them apart by listening more carefully. The lesson is not only about objects, it is about attention. It is about the humility to admit that a shadow can carry multiple meanings, and the patience to wait for the right instrument to reveal which one it wears. Then practice changes. Catalogues are relabeled, asterisks bloom beside famous entries. Candidate Gravastar becomes a phrase that no longer provokes a smile. Observers begin to time their campaigns to catch the faint reflections that an accretion flow might send back after touching a surface. Theorists refine the equations of exotic shells no longer as speculative art, but as engineering for predictions that can be falsified tomorrow. Funding panels shift, curricula adjust. The story we tell about collapse writes a new chapter in the same book, and yet even with echoes in hand, certainty remains a horizon we never quite cross. Some mergers will still sing like perfect black holes. Some shadows will match predictions so precisely that no surface can be justified. The universe will keep both faces trickster and monster, and we will learn when each appears. This is not a defeat. It is a widening. It is the cosmos reminding us that plurality is not weakness that reality often chooses and where we hoped for, or in the quiet after the first press conferences, the questions turn deeper. If shells exist, how do they form in detail? How do they store memory without spilling it, or do they spill a little? And is that why we heard them? Do their interiors change with time, cooling, crystallizing, perhaps dreaming new physics we can never access? Can a surface that elegant survive the battering of a messy universe for billions of years? The mystery does not shrink. It grows, but with cleaner edges like a coastline coming into focus as the fog lifts. One more image lingers. A technician alone at a console at 3 a.m, the building empty, the graphs still glowing. On the screen, the Echo series lines up again, faint as breath on glass. The technician leans back, closes his tired eyes, and for a moment thinks of seashells. Hold one to your ear and you hear a ghost of the ocean that shaped it. Hold a Gravastar to the sky and you hear a ghost of the universe shaping itself. The metaphor is imperfect, as all metaphors are, but it is enough to carry the feeling forward into the next day's work, because that is where the story always returns. To work, to better detectors, steadier baselines, sharper images, longer patience, to the discipline of not rushing the wonder and not letting wonder slip away. If the echoes are real, they are an invitation. If some shadows hide hollows, they are not an ending. They are an opening. They say, keep listening, keep asking, keep the balance between gravity and grace. At the end of this long journey through shadows and hollows, one truth stands above all. The universe is not finished surprising us. For generations we believed that the darkest objects in the cosmos were black holes, places where gravity triumphs so completely that even light could not escape. We imagined them as cosmic monsters, as final punctuation marks in the story of stars. Yet the Gravastar whispers that perhaps the universe does not write endings so abruptly. Perhaps every shadow hides a second possibility. If Gravastars exist, they reveal a cosmos that resists annihilation. They show us that even at the brink of collapse, nature finds ways to preserve memory, to balance extremes, to avoid infinities. They transform what seemed like an abyss into a vault, what seemed like destruction into continuity. And if they do not exist, then black holes stand all the taller monuments to gravity's unforgiving strength, teaching us humility in the face of finality. Either way we win, either way the night sky teaches us. For science, Gravastars are not only a hypothesis, but a discipline. They remind us that skepticism and imagination are partners, not enemies. To dream of exotic shells and hollow stars is to push against the boundaries of what is known. To test those dreams with data, with detectors that listen to space-time and telescopes that sketch shadows across the void, is to keep our feet on the ground even as our eyes are fixed on the infinite. Gravastars are both myth and measurement, both metaphor and mathematics. For culture they are new symbols. Where black holes taught us fear of loss, Gravastars teach us hope of preservation. Where black holes stood for annihilation, Gravastars stand for memory. They offer us a story of hollowness that is not emptiness but potential of silence, that is not void but archive. They turn the cosmos into a cathedral where even collapse becomes continuity, where even endings hold seeds of new beginnings. And for us as individuals staring up at the stars, Gravastars change the way we feel about our own lives. They remind us that behind every mask lies a mystery that every shadow may conceal, not destruction, but transformation. They whisper that the universe itself refuses to forget that every spark leaves its trace, that even in the deepest darkness there is structure, balance, and meaning. So the next time you look at the night sky and see the faint glow of the Milky Way, think of the shadows hidden there. Some may be black holes relentless and merciless. Some may be Gravastars' hollow vaults of memory wearing the mask of monsters. And some may be things we have not yet dreamed of. Each one is a reminder that the story of the universe is not finished, that the script is still being written, that we are part of a drama larger than imagination. The cosmos is not only vast, it is clever. It hides it, deceives it, transforms. And whether Gravastars prove real or not, they have already given us a gift. The courage to keep asking, the patience to keep listening, and the wonder to keep looking beyond the obvious. Thank you for joining me on this journey through shadows, hollows, and possibilities. Stay with me because the universe is not done telling its story, and neither are we. We live inside a bubble. It is invisible, enormous, and absolute. This bubble is not made of glass or matter, but of light itself. Beyond its edge, the universe continues filled with galaxies, stars, and perhaps infinite wonders. Yet we cannot see them, cannot reach them, cannot even prove they are there. The edge of our bubble is the farthest that light has had time to travel since the birth of everything. It is called the observable universe, and it is the wall that mocks every ambition we have to explore. The paradox is immediate. The universe may be infinite, but to us it is bounded. On Earth, explorers once faced oceans that seemed endless horizons that promised new worlds and frontiers that eventually yielded to courage and sail. But in space, our horizon is not a distance we can cross. It is a barrier set by the speed of light, a speed that no machine or mind can overtake. We are like sailors trapped on an island watching waves that never carry us closer to the shore beyond. Let us for a moment imagine that we dare to attempt the impossible. What would it take to travel to the other side of the universe? Could we build a ship capable of outrunning time itself? Could we fold the fabric of space-time into a bridge? Or could there be a loophole hidden in the strange rules of the quantum world? These are not idle questions. They cut to the heart of what we know and what we cannot yet know about reality. The first challenge is simple to state but impossible to solve. Nothing, according to Einstein's theory of relativity, can move faster than light in a vacuum. A beam of light travels at 300,000 kilometers per second, and that is the ultimate speed limit. The faster we accelerate toward it, the harder the laws of physics push back. Mass increases, energy demands soar, and time itself begins to distort. For a traveller moving near the speed of light, moments stretch and twist. A journey that seems to take centuries from the outside might pass in a handful of years for those aboard. This effect, called time dilation, is not science fiction. It has been measured with clocks on airplanes, with satellites orbiting Earth, with particles racing in accelerators. So in principle, yes, we could build a vessel that approaches the speed of light, and for its crew, entire galaxies might slip by within a lifetime. But here lies the cruel twist. The universe itself is expanding. Space is not a stage where actors move, but a fabric that stretches. Galaxies at the edge of our sight are receding faster than light itself, carried away by the expansion of space-time. No matter how fast we travel, the finish line runs ahead, always out of reach. The other side of the universe is not a fixed destination. It is a moving horizon, like a mirage that recedes as we chase it. This realization is devastating, but it does not end the story. If speed cannot take us there, perhaps geometry can. Einstein's equations, written more than a century ago, describe how matter and energy bend the shape of space-time. Under the right conditions, space-time can fold back on itself, creating shortcuts we call wormholes. Imagine a tunnel carved through the fabric of reality, linking two distant regions as easily as a subway links neighborhoods of a city. In theory, stepping through one end could deliver you instantly to the far side of the cosmos. It sounds like magic, but it is mathematics. The equations admit the possibility, yet they also demand a price. To hold a wormhole open to prevent it from collapsing into nothing requires something nature may not provide. Exotic matter with negative energy density. This is not ordinary material. It is not fuel rock or plasma. It is matter that would behave in ways utterly alien, pushing instead of pulling, repelling instead of attracting. Without it, the tunnel collapses before anything can pass through. The hunt for negative energy is not hopeless. A faint whisper of it has already been glimpsed in the laboratory, in an effect called the Casimir force. Place two metal plates very close together in a vacuum and quantum fluctuations push them inward. The vacuum itself exerts a pressure hinting that energy can be less than zero, but the amounts are vanishingly small, far from what would be needed to stabilize a cosmic passage. So once again the dream retreats. We are left stranded inside our bubble, tantalized by the mathematics of wormholes, denied by the physics of matter. And yet, just as our despair deepens, a new possibility emerges from the smallest scales of all. Quantum mechanics does not treat space-time as smooth and continuous. At the tiniest dimensions, reality froths and foams. Space itself may flicker, twisting into bubbles, tunnels, and fleeting connections. Perhaps the universe is already filled with wormholes, microscopic, unstable, vanishing before anything can enter. If that is true, then the cosmos is riddled with invisible doors, locked but not destroyed. The challenge is not their existence, but our ignorance of how to use them. Could an advanced civilization reach into the quantum foam, seize a tiny wormhole, and stretch it like a balloon until it became a gateway? Could that be the path to the far side? We do not know. We cannot know yet. What we do know is that the universe has a habit of tempting us with paradoxes. It shows us the key in equations, then hides it in physics. It whispers that there may be roads across infinity, then bars them with conditions we cannot meet. And so we are left on the edge of mystery, peering outward from our fragile bubble of light. And that is where our journey truly begins. At the smallest scales of existence, the smooth stage of space-time dissolves into chaos. Physicists call it the quantum foam, a restless sea where uncertainty rules, and the very geometry of the cosmos flickers like static. To us the vacuum looks empty, but emptiness is an illusion. Virtual particles burst into being and vanish almost instantly. Energy fluctuates, distances blur, and causality itself begins to tremble. Here in this microscopic storm, wormholes may already exist. Not the massive tunnels imagined in science fiction, but tiny unstable channels flickering into and out of existence in less than a heartbeat. They are the scars of uncertainty forming and collapsing faster than light can cross them. For us, they are useless, but to nature they are reminders that reality is not fixed, that space and time may be far stranger than our senses allow. The dream then is to catch one. Imagine capturing a microscopic wormhole before it vanishes, stabilizing it with exotic energy, and inflating it until it could swallow a starship. The idea is audacious, almost absurd, yet not forbidden by mathematics. The physicist Kip Thorne once speculated about such possibilities, suggesting that wormholes might be engineered if we could manipulate quantum fields with enough precision. It would be like grabbing a bubble from boiling water and freezing it before it bursts. If that could be done, the bubble could grow into a tunnel large enough to step through. But theory punishes imagination with cost. To hold open such a passage, negative energy must be supplied in quantities far beyond anything we can generate. The Casimir effect offers a glimpse, but it is the faintest whisper of what would be needed. The gulf between laboratory trickles and cosmic rivers is vast, perhaps uncrossable. Our most advanced particle accelerators barely scratch the surface of what would be required. Still, the idea refuses to die. The existence of dark energy itself, an unknown force driving cosmic expansion, hints that the universe is capable of producing negative pressure on unimaginable scales. Could there be a link between the engine of cosmic acceleration and the exotic matter demanded by wormholes? If dark energy is the backdrop of the universe, then perhaps it is the very ingredient we need hiding in plain sight. We just do not yet know how to shape it. And this leads us to another paradox. The same dark energy that might permit us to construct shortcuts is also the force pulling the universe apart, carrying galaxies beyond our reach. It is both our captor and our potential liberator. Harnessing it would mean taming the very expansion that imprisons us, a feat that makes the construction of rockets or even fusion engines seem trivial in comparison. Suppose, though, that we succeed. Suppose some civilization, human or otherwise, manages to master the quantum foam inflate wormholes and lace the cosmos with tunnels. The far side of the universe could then be a step away. But the story does not end with triumph, for relativity is not done with us. Wormholes are not just passages through space. They are passages through time. A stable wormhole manipulated in the right way could become a time machine. If one mouth is accelerated near the speed of light and then returned, the two ends become unsynchronized by time dilation. Enter one end and you could emerge not only elsewhere but elsewhen. The laws of physics appear to allow this. The implications are staggering. The paradoxes unfold instantly. If I step through and arrive before I leave, can I prevent myself from ever travelling? If so, who then emerges? Such questions gnaw at causality, shredding the idea of consistent history. Physicist Igor Novikov proposed a resolution. Perhaps the universe enforces consistency, allowing only loops where the past cannot be changed. But Stephen Hawking suggested something harsher, a chronology protection principle, an invisible safeguard preventing time machines from ever forming. According to him, the universe itself despises paradoxes and would erase them before they arise. If Hawking is right, then every attempt to stabilize a wormhole would collapse under the weight of quantum fluctuations, destroying the machine before it could be used. Time travel would remain a mirage, always visible in theory but forbidden in practice. If Novikov is right, then time travel might occur, but only in ways that lock us into unbreakable loops, robbing us of freedom to change the past. Either way, the dream of using wormholes to cross the cosmos is shadowed by consequences we may not be willing to face. To reach the other side of the universe, we may be forced to tamper with time itself, and time is a thread that resists being pulled. Yet the paradox does not extinguish wonder, instead it sharpens it. If the universe teases us with the possibility of shortcuts, even impossible ones, then perhaps the deeper message is that we have not yet uncovered the full set of rules. Physics is not finished. Relativity and quantum mechanics are masterpieces, but they are incomplete. Somewhere hidden in the fabric of reality is a deeper law that unites them. Until we find it, the road to the far side remains closed. And so we stand at a threshold. On one side is everything we know, rockets' relativity expansion horizons. On the other side is everything we cannot yet imagine. Wormholes' quantum gravity, perhaps new dimensions. Between them lies ignorance, the most formidable barrier of all. Imagine for a moment that we somehow bypass all the obstacles. We discover exotic matter, stabilize wormholes, and create a network of tunnels spanning the universe. The dream is realized. The other side is within reach. But relativity does not surrender so easily. Inside the equations lurks a trap, one that makes even victory taste like defeat. Wormholes, no matter how carefully engineered, are not gentle places. The gravity that shapes them is ferocious, curving space-time so sharply that even the slightest imbalance can destroy the tunnel. Any traveller who dares to enter risks being torn apart by tidal forces stretched into threads of atoms in a process called spaghettification. What science fiction depicts as smooth corridors of light might in reality be chaotic maelstroms of distortion, with energy densities so extreme that no material we know could survive them. Even worse, wormholes are unstable. According to calculations, they collapse faster than light could travel through them. By the time a ship even begins its journey, the passage has already pinched shut. The only way to hold it open is to continuously feed it negative energy in amounts that dwarf the output of entire stars. It is like trying to keep a bridge from crumbling by pouring oceans into its foundations every second. And if somehow the wormhole remains open, new dangers emerge. Closed time-like curves pass through space-time that loop back into the past are a natural consequence. Step through the wrong way and you may arrive before you left. Cause and effect unravel, leaving paradoxes in their wake. The universe, it seems, resists being cheated. This has led some physicists to a sobering conclusion. Wormholes may exist but not for travel. They may form and vanish in the quantum foam or lurk inside black holes, but they remain out of reach like forbidden passages glimpsed in dreams. The mathematics teases us, but the physics denies us. Yet the dream does not end here because the universe has other secrets. Black holes themselves, those engines of destruction, might hint at ways across the cosmos. When Einstein and Nathan Rosen first explored their equations in the 1930s, they discovered that the mathematics of a black hole naturally connected to a white hole, a hypothetical object that ejects matter instead of swallowing it. Together they formed what became known as the Einstein-Rosen bridge, a wormhole born not from speculation but from the structure of relativity itself. If such bridges exist, then falling into a black hole might not be the end but the beginning of a journey. On the far side, matter could re-emerge from a white hole in another region of space, perhaps even another universe. It is a vision at once terrifying and exhilarating. The most violent objects in the cosmos transformed into cosmic gateways. But nature does not seem to play along. Real black holes are not eternal mathematical constructs. They form from collapsing stars, and their interiors are not stable bridges but singularities points. Where density becomes infinite and known physics breaks down. Anything that crosses the event horizon is doomed, not transported. The bridge collapses before it can be crossed. Still, the idea lingers. In the mathematics of relativity, bridges are possible. In the harsh reality of astrophysics, they are not. But between these two lies a gap, and in the gap might be the key. What if black holes are not merely destructive? What if under conditions we do not yet understand they really are connected to something else? This speculation gains fuel from the mystery of information. According to classical physics, anything that falls into a black hole is lost forever. But quantum theory insists that information cannot be destroyed. This contradiction, the black hole information paradox, has haunted physics for decades. If information does escape, then perhaps black holes are not tombs but gateways leaking clues to a larger reality. Could it be that the other side of the universe is hidden not across vast distances, but within the very objects we fear most? Could black holes be doors disguised as prisons? If so, then the path to the far side may not lie in outrunning expansion or bending geometry, but in understanding what truly happens beyond the event horizon. And that question, the fate of information, the reality of black hole interiors, leads us to the frontier of modern physics. To answer it, we must confront quantum gravity, the long-sought theory that unites relativity and quantum mechanics. Without it, our visions remain speculation. With it, the truth may finally be revealed. The far side of the universe might not be a place we can sail to like an ocean. It might be hidden in the very structure of space and time, waiting for us to decipher the language of reality itself. And so the journey continues deeper into the paradox of horizons. When we gaze into the night sky, we imagine the stars and galaxies as if they are arranged on a vast cosmic map. But this map is deceptive. Every point of light we see is not what it is, but what it was. Light takes time to travel, and the farther we look, the older the message becomes. The most distant galaxies appear to us not as they are today, but as they were billions of years ago. The deeper we peer, the younger the universe looks, until eventually we reach a time when galaxies had only just begun to form. The James Webb Space Telescope has allowed us to push this vision to its limit. With its infrared eyes, Webb peers through cosmic dust and across billions of light years, revealing galaxies from a time less than 1 billion years after the Big Bang. What it sees is astonishing. Instead of a sparse cosmos of tiny fragile structures, Webb has found massive galaxies, brilliant with stars and supermassive black holes lurking at their hearts. These should not exist so early, not according to our models. Their presence suggests that either galaxies grow faster than we thought, or that our understanding of cosmic evolution is incomplete. But even Webb has a limit. Beyond a certain distance, light cannot reach us at all, no matter how powerful our instruments. This distance is set not by our technology, but by the age of the universe and the speed of light. We cannot see beyond the cosmic horizon because there has not been enough time for that light to arrive. The other side is hidden behind time itself. This horizon is not just a matter of sight, it is a matter of causality. Beyond it, events are disconnected from us. No signal, no ship, no message could ever cross the gulf. Those regions might as well belong to another reality forever sealed away. And yet they exist. Their gravity tugs faintly on what we can see. Their structures shape the universe indirectly, but they remain beyond our grasp. It is here that the mystery deepens. If the universe is infinite, then the other side is simply more of the same galaxies stretching endlessly, structures repeating without end. But if the universe is finite, then the other side might not exist in the way we imagine. The cosmos could wrap back on itself like the surface of a sphere, travel far enough in one direction, and you might return from the other just as a ship circling Earth arrives where it began. In such a universe, the other side is not a distant land, but the very place you started approached from behind. Astronomers have searched for evidence of such curvature. They study the cosmic microwave background, the afterglow of the Big Bang, mapping its faint ripples in exquisite detail. If the universe were curved like a sphere or a donut, patterns would repeat circles in the sky, would match, echoes would appear. So far, the evidence suggests that space is flat or nearly so, extending without curvature. But flat does not mean infinite. It may still be finite, like the surface of a vast sheet folded in ways we cannot see. If this is true, then the other side of the universe is not unreachable. It is an illusion. There is no edge to cross because every path eventually loops back. The horizon is not a boundary, but a trick of perspective created by the marriage of light and time. Yet there is another possibility stranger still. Our universe may not be the only one. The equations of inflation, the rapid expansion that occurred fractions of a second after the Big Bang, suggest that our bubble of reality may be just one among countless others. If so, the other side might not be across space, but across universes. Parallel realms could exist beyond our horizon, each with different laws of physics, different histories, perhaps even different versions of us. If wormholes or quantum fluctuations connect these realms, then the other side of the universe is not just unreachable, it is unrecognizable. We may expect galaxies and stars, but instead find realities where gravity repels, where time flows differently, where matter itself does not exist. The other side might not be the destination we imagine. It might be alien beyond comprehension. And this leaves us with a profound question. What do we really mean by the other side? Is it simply more galaxies hidden beyond our horizon? Or is it an entirely different order of reality, a multiverse of infinite variation? The answer is unknown. But the pursuit itself reshapes our understanding, turning the unreachable into a mirror of our ignorance and our curiosity. The other side of the universe is less a place and more a challenge, a reminder that we have only just begun to decipher the code of existence. And as we stand on this horizon staring outward into the unknown, we are faced with the possibility that the most profound discoveries lie not across space, but in the laws that govern it. If the other side of the universe is hidden behind horizons, then perhaps the path to it lies not in distance, but in understanding those horizons themselves. One of the strangest discoveries of modern cosmology is that horizons are not merely observational limits. They are physical boundaries woven into the laws of reality, shaping what is possible and what is forbidden. Consider the event horizon of a black hole. It is not a surface of matter, but a boundary in space-time. Cross it and escape becomes impossible. Information is trapped, light itself cannot return, and to outside observers, time appears to freeze. The black hole event horizon is a cousin of our cosmic horizon, both defined by light and the inability of signals to cross. In one case, gravity pulls so strongly that escape is denied. In the other, expansion carries galaxies away faster than light can bridge the gap. In both, the horizon is a point of no return. But unlike the event horizon of a black hole, the cosmic horizon is not absolute for everything. Galaxies beyond it continue to exist. Their light may never reach us, but their gravitational influence can still shape the universe. In fact, subtle patterns in the cosmic microwave background suggest that what lies beyond our horizon has left its fingerprints. The unseen still affects the seen like a ghost pressing against the fabric of our reality. This raises a provocative idea. What if the far side of the universe is not truly cut off but only hidden? Could we use something other than light to glimpse it? Gravitational waves, ripples in space-time itself offer such a possibility. Unlike light, they interact so weakly with matter that they can cross barriers that photons cannot. Detectors like LIGO and Virgo have already caught these whispers from colliding black holes and neutron stars. In principle, gravitational waves from the earliest moments of the Big Bang could carry information from beyond the light horizon, from times and places we thought forever unreachable. If we could detect such primordial waves, we might glimpse a snapshot of the universe before light itself could travel freely. It would not be the far side in space, but the far side in time. And perhaps hidden in their delicate vibrations lies evidence of what lies beyond our bubble. Still, the gulf remains. Even if information leaks through, even if subtle signals betray the presence of distant realms, travel is another matter. To physically cross is to fight expansion itself. Here we encounter one of the most unsettling truths of cosmology. The universe is not just expanding, it is accelerating. Galaxies are not only receding, they are speeding up. The more distant they are, the faster they run. Beyond a certain threshold, they vanish forever, receding faster than light. This is not a temporary state. It is the long-term fate of our cosmos driven by the mysterious force we call dark energy. Dark energy is perhaps the most baffling discovery of the last century. It makes up nearly 70% of the universe, yet we do not know what it is. We know only what it does. It pushes relentlessly, counteracting gravity, stretching the fabric of space. Without it, the expansion of the universe would slow. With it, the expansion accelerates, turning horizons into permanent barriers. The irony is painful. Dark energy imprisons us within our observable bubble, sealing the far side forever, and yet it may also hold the key to crossing it. If we could understand its nature, manipulate it, even harness it, we might gain control over space-time itself. Dark energy is both jailer and potential liberator, but at present it remains a mystery, perhaps the greatest in all of physics. This leaves us with a haunting vision of the future. As billions of years pass, galaxies slip beyond our horizon one by one. The night sky grows emptier. Eventually only our own local group of galaxies will remain bound together by gravity while the rest vanish into darkness. To future astronomers, the universe will appear small, finite, isolated. They will not even know that other galaxies once existed. The far side will be erased not only from view, but from memory. We living now are in a privileged position. We can still see the great expanse, still measure the expansion, still sense the enormity of what lies beyond. We are perhaps the only generation of cosmic observers who can grasp the scale of the universe in its fullness, before most of it disappears forever beyond the horizon. And so the question burns brighter. Could we find a way to cross the gulf before it is too late? Could we outwit dark energy, tame the expansion, or cheat the laws that confine us? The answer remains hidden, but the urgency grows. The horizon is not only a mystery, it is a countdown. If horizons limit us, then perhaps the solution is not to cross them, but to change them. The idea sounds impossible, almost arrogant, yet it emerges naturally when we ask a daring question. What if we could reshape space-time itself? In 1994, physicist Miguel Alcubierre proposed a radical concept now known as the Alcubierre drive. The idea is simple to describe, yet staggering in implication. Instead of pushing a ship through space faster than light bend space around the ship, compress space-time in front, expand it behind, and let the vessel ride a wave of distorted geometry. Inside its bubble, the ship would never exceed light speed relative to its immediate surroundings, keeping relativity intact. But to an external observer, the bubble itself could move faster than light, carrying its contents across unimaginable distances in short spans of time. This concept became famous as the warp drive, echoing science fiction dreams. But unlike fiction, Alcubierre's mathematics were real, drawn from Einstein's equations themselves. The drive is not forbidden by relativity. The catch, of course, is the same ghost that haunts wormholes: negative energy. To create and sustain the bubble, one must manipulate exotic matter on scales beyond comprehension. Early estimates suggested that the energy equivalent of the entire observable universe might be required to move a single ship. Later refinements reduced the number, but even the most optimistic versions still demand resources far beyond anything humanity could muster. Yet the vision endures because it reshapes the problem. Instead of breaking the light speed limit, we avoid it. Instead of chasing galaxies as they flee, we bend the track beneath us. If negative energy can be mastered, then the far side of the universe is no longer a forbidden dream. It becomes a reachable destination. The challenges are immense, but the concept carries an important lesson. Horizons are not immovable walls. They are features of space-time, and space-time is malleable. If we learn to sculpt it, we may discover paths where none exist today. But bending space may not be the only path. Theories of higher dimensions suggest that our universe might be just one slice of a larger reality. String theory, for instance, describes the fundamental particles not as points, but as vibrating strings whose harmonies require extra dimensions curled up beyond our perception. If those dimensions can be unfolded or accessed, then shortcuts through them might bypass the limitations of our three-dimensional space. In such a scenario, the far side of the universe could be only a small step away in a higher dimensional landscape. These ideas remain speculative, untested, and controversial. Critics argue that without experimental evidence, higher dimensions and warp drives are nothing more than mathematical fantasies. Yet history has shown that imagination often precedes discovery. Once black holes were dismissed as absurdities of theory. Today we image their shadows with telescopes spanning the Earth. Once gravitational waves were considered too faint to detect. Today they are recorded routinely. What seems impossible in one century may become routine in the next. Still, there is a danger in hope. For every breakthrough that reshapes our view, countless dreams remain unrealized. Anti-gravity, perpetual motion, faster than light communication. All have been imagined and none have been achieved. The cosmos is not obligated to yield to our desires. The other side of the universe may remain forever hidden no matter how clever our theories, and yet to abandon the pursuit is to betray curiosity itself. The impossible challenges us not because they promise success, but because they reveal the boundaries of what is known. In probing those boundaries, we discover more than answers. We discover who we are, beings who refuse to accept walls without first testing them. Perhaps one day, long after our civilization has evolved beyond recognition, descendants of our species or minds we cannot even imagine will wield the tools to manipulate space-time as easily as we now sail oceans. To them, horizons may be mere inconveniences, the far side of the universe, no more distant than another city is to us. Whether or not that day comes, the seeds of it lie here in our restless need to ask if the journey is possible. The universe is not static. It is a dynamic arena, restless and evolving. Galaxies form stars, ignite planets, coalesce black holes, devour, and everywhere in between, space itself stretches. This expansion is the great thief of horizons, stealing galaxies from our view one by one, and yet it is also the great sculptor shaping the very fabric we hope to traverse. To talk about reaching the other side of the universe without confronting cosmic expansion is to ignore the stage upon which the drama unfolds. When Edwin Hubble first discovered in the 1920s that galaxies were receding from us, the picture was startling but simple. Space was stretching, and the farther away something was, the faster it fled. At first, it seemed that gravity might slow this expansion. Perhaps one day the universe would halt, then reverse, collapsing into a fiery end known as the Big Crunch. But in the late 1990s, new evidence shattered that expectation. Observations of distant supernovae revealed that the expansion is not slowing down. It is accelerating. Some unknown force, dubbed dark energy, is driving galaxies apart at an ever-increasing pace. This changes everything. With acceleration, horizons are no longer temporary. They become permanent. Beyond a certain distance, galaxies are carried away faster than light, forever disconnected. The more time passes, the closer that horizon creeps. Eventually, only the small cluster of galaxies bound to our own will remain visible. All else will fade into darkness. For those who dream of travel, this is devastating. No matter how advanced a starship we build, no matter how clever our engineering, the expansion ensures that the vast majority of the universe will slip beyond our reach. The finish line is not just far away, it is moving faster than we can ever hope to chase. The far side is receding into a void we cannot conquer, and yet there is a strange comfort hidden here. If the horizon is set by the speed of light and the power of expansion, then it is not a fixed wall but a dynamic boundary. It defines what is possible now, not what will be possible forever. If we could one day manipulate dark energy itself, perhaps we could rewrite the rules of expansion. The far side would not vanish, it would reappear. This is not pure fantasy. We already know that the universe is governed by quantum fields, invisible scaffolds that fill all of space. Dark energy may be one such field. If so, it is not unreachable. It is part of the very vacuum between atoms woven into the same reality we inhabit. We may not yet know how to touch it, but its fingerprints are everywhere. The challenge is not its existence, but our ignorance. There is another implication darker still. If dark energy grows stronger with time, then the expansion may not simply continue. It may accelerate without end, tearing galaxies apart, then stars, then planets, then even atoms in a final disintegration called the Big Rip. If that fate awaits, then travel to the other side of the universe is not just difficult, it is doomed. There would be no other side to reach, only fragments dissolving into the vacuum. But fate is not yet sealed. Our measurements of dark energy are still crude, our models still uncertain. For now, the evidence points to a constant, steady push. If that is true, then the universe will expand forever, cooling into heat death. A future of darkness, silence, and emptiness. The other side of the universe in that scenario becomes not a place but an absence. Still, in our age, we remain privileged. We live at a cosmic moment when the universe is vast and visible, when horizons stretch far and galaxies fill the sky. We can ask the question with wonder: what lies beyond? Future civilizations may never even know to ask. To them, the sky will reveal only isolation. The far side will be erased from history itself. That realization gives urgency to our quest. We are the observers standing at the edge of possibility, with tools powerful enough to glimpse the cosmos in its glory. If the universe is to teach us its secrets, it must be now before the curtain falls. And so, the dream of travelling to the other side is not just about exploration, it is about seizing a moment in cosmic history when the universe is still open to us. When we imagine the other side of the universe, we picture distant galaxies glittering in unreachable darkness. Yet the deeper puzzle is not distance, it is time. Every photon that reaches our telescopes is ancient, travelling across billions of years. The farther we look, the younger the universe appears, until eventually we confront the first light itself, the cosmic microwave background, a faint glow released when the universe was only 380,000 years old. Beyond that glow lies a fog through which no light can pass. This makes the far side of the universe not just invisible but hidden behind the memory of creation. The cosmic microwave background is a wall painted with the fingerprints of the Big Bang. Its ripples reveal the seeds of galaxies, the distribution of matter, the geometry of space itself. But it is also a veil. We cannot peer beyond it with light no matter how powerful our instruments become. And yet scientists have begun to dream of other messengers. Gravitational waves, those ripples in space-time itself, may carry information from earlier times. Unlike light, they pass unhindered through matter. If detectors sensitive enough could be built, they might capture echoes from the first instance of the universe. Signals from an era when space-time expanded at a speed beyond comprehension during cosmic inflation. Such waves could reveal not only what lies behind the microwave background, but whether our universe is just one bubble among many. This is where the concept of the multiverse enters the stage. Inflation theory, while explaining the large-scale uniformity of the cosmos, also suggests that inflation may not have ended everywhere. Instead, it may continue eternally spawning countless bubble universes. If this is true, then the other side of our universe is not across space, but across realities. Our observable bubble is one among countless others, each potentially with different physical laws. In one, gravity might be stronger. In another, atoms might never form. In yet another, stars might burn out in moments, leaving darkness behind. Could we ever reach such realms? In principle, eternal inflation suggests that new universes form with horizons separating them. If wormholes or quantum fluctuations could link these bubbles, then travel between universes might be possible. But here the paradox grows deeper. The energy scales of inflation dwarf anything we can imagine far beyond the reach of engineering. To manipulate such forces would be to wield the power of creation itself. For now, the multiverse remains a mathematical whisper, a speculation born from equations and inference, not observation. Still, it teases us with possibility. If the far side of our universe is forever sealed, perhaps the real escape lies in leaving it altogether. Perhaps civilizations more advanced than ours, if they exist, have already walked this path, slipping between bubbles, migrating not across galaxies but across universes. If so, then our dream of crossing to the other side may already have been fulfilled elsewhere by minds we cannot imagine. But speculation carries its own danger. For centuries, humans believed the Earth was the centre of everything. Later, we believed the Milky Way was the whole cosmos. Each time discovery humbled us. Perhaps the idea of crossing universes is simply the latest illusion, another projection of our longing for escape. Perhaps the truth is harsher. We are bound to our bubble forever, unable to reach even its edge, let alone what lies beyond. Yet the act of asking reshapes science. To test the multiverse, physicists hunt for subtle signatures, collisions between bubbles imprinted on the cosmic microwave background, unexplained anomalies in temperature patterns or hints of exotic particles leaking from beyond. None have yet been confirmed, but the search itself drives technology forward, refining our instruments and sharpening our theories. Even failure brings progress. So the far side of the universe becomes both unreachable and indispensable. It is a paradox that fuels inquiry. We cannot travel there yet in seeking to understand it. We deepen our grasp of physics, time, and existence. The horizon is less a wall than a teacher. It denies us access but offers knowledge in return. If the multiverse tempts us with endless possibilities, black holes confront us with ultimate boundaries. They are cosmic prisons where gravity reigns supreme, swallowing everything that dares to cross their horizons. And yet, in the paradoxical way of the universe, these engines of destruction may also hint at escape routes. The equations of general relativity describe black holes with uncanny precision. They predict event horizons, singularities, and the warping of time itself. But tucked within the mathematics are structures called Einstein-Rosen bridges. These bridges connect a black hole to a hypothetical white hole, a mirror object that expels matter instead of devouring it. Together they form a wormhole, a tunnel through space-time. If stable, such a bridge could serve as a shortcut across the cosmos, perhaps even a path to the other side of the universe. The problem is stability. Real black holes are messy. They spin, they grow, they evaporate through Hawking radiation. None of them appear to host neat tunnels. The bridges collapse too quickly, pinching off before anything could pass through. The singularity at their heart shreds information, leaving us with paradoxes that pit relativity against quantum mechanics. And yet the very struggle to resolve these paradoxes may reveal something profound. Consider the black hole information problem. According to relativity, information that falls into a black hole is lost forever. But quantum theory insists information cannot be destroyed. Both theories cannot be correct, and reconciling them demands a deeper law, quantum gravity. Some proposals suggest that information leaks out in subtle ways encoded in Hawking radiation. Others argue that the interior of a black hole is connected to the outside through hidden geometry, perhaps even wormholes too small to detect. If so, then black holes are not prisons at all, but gateways revealing that space-time is more interconnected than we realize. There are even bolder ideas. The holographic principle suggests that all the information in a region of space can be described by data encoded on its boundary like a cosmic projection. If this is true, then our entire universe may be a hologram with reality itself, emerging from information inscribed on horizons. In such a picture, the other side of the universe may not be across distance, but across layers of information woven into the fabric of existence. These ideas are not proven, but they are more than speculation. They are attempts to solve contradictions, to bridge the gap between two of the greatest achievements of science, relativity and quantum mechanics. If successful, they may unlock not only the mystery of black holes, but the deeper nature of reality. And once again, horizons reveal their double role. They confine us, denying access, yet they also teach us, forcing us to probe deeper. A black hole's event horizon and the cosmic horizon may be different in scale, but they are united in spirit. Both are limits that hide the unknown, daring us to uncover it. Could the key to reaching the other side of the universe lie in understanding black holes? Perhaps. If they truly connect to other regions of space-time, then they may already be natural wormholes. We cannot survive the journey now, but maybe future physics will reveal ways to navigate their interiors. Or maybe the truth is even stranger, that black holes do not lead elsewhere in space, but elsewhere in reality, to domains we cannot yet describe. The irony is sharp. The darkest objects in the universe may hold the brightest clues to its structure. The very prisons we fear may be the doors we seek. To solve their riddle is to take a step toward the far side of the universe, not by crossing it, but by transforming our understanding of what side even means. And so the black hole, once a symbol of doom, becomes a symbol of possibility. If we dare to follow its mystery, we may discover that the other side is closer than we think, hidden not in distant galaxies, but in the geometry of reality itself. Every journey has a map, but in cosmology, the map itself is an illusion. When we chart the universe, we imagine a frozen snapshot, galaxies scattered like islands across a vast ocean. Yet the reality is stranger. What we see is not the universe as it is, but as it was. Every photon carries a delay, a record of ancient history. The farther we look, the deeper into the past we peer. This distortion means that our cosmic map is layered with time. Nearby galaxies show us the present, but the faintest smudges of light are fossils from billions of years ago. When we study them, we are not seeing neighbours across space, but ancestors across epochs. The other side of the universe is not just far away. It is elsewhere, hidden in the flow of time itself. This idea reshapes the meaning of travel. To reach the far side is not simply to cover distance. It is to cross ages. A voyage outward is a voyage backward, a trek not just across kilometres, but across billions of years. The destination is not a place waiting for us, but a time that has already vanished. Even if we could step across instantly, what we would find is not the universe now, but the universe then. The James Webb Space Telescope has already given us glimpses of this temporal paradox. It has revealed galaxies so massive, so luminous, that they defy our models of early cosmic history. According to our theories, such giants should not have formed so quickly. Yet Webb shows them blazing less than 1 billion years after the Big Bang. They are ghosts of the young universe messengers from an era that should not exist. If these galaxies can exist, then our understanding of time growth and structure may be incomplete. Perhaps matter clumped faster than we thought. Perhaps the laws of physics operated differently in the early universe. Or perhaps our models of cosmic expansion need revision. Whatever the answer, it reveals that the far side of the universe is not just about where we cannot go, it is about what we do not yet understand. There is a haunting implication here. If travel outward is travel backward, then to reach the true other side, the universe as it exists now, beyond our horizon, we would need to overtake time itself. We would need to arrive faster than light, faster than causality, into regions whose present is forever disconnected from ours. It is not simply forbidden, it is meaningless. For us, the other side does not exist as a simultaneous place. It exists only as a memory we cannot access. And yet this impossibility does not end the story. It deepens it. By studying the past, we infer the present. By mapping ancient light, we deduce what must be unfolding beyond our horizon. Through simulations, through mathematics, through observation, we reconstruct the unseen. The far side may remain hidden, but its influence leaks into what we can measure. This is where cosmology becomes detective work. We measure the faint anisotropies in the cosmic microwave background. We map the distribution of galaxies across billions of light years. We study the large-scale structure of the universe, the cosmic web of filaments and voids. From these clues, we infer what lies beyond painting a picture of the unseen with equations and models. It is not direct travel, but intellectual travel, a journey across thought. As we pursue the far side of the universe, we inevitably confront the question of limits. Not technological limits, but fundamental ones. The universe is governed by laws that appear unbreakable. Yet throughout history, many of those laws have been challenged, stretched, or redefined. Once we believed the Earth was the center of everything. Once we believed time flowed the same for all observers. Once we believed atoms were indivisible. Each belief fell when confronted with deeper truth. Could the speed of light, the absolute horizon, also be one day overturned? Some physicists argue that it cannot, that the light speed barrier is as permanent as logic itself. Others suggest that under quantum gravity exceptions may appear. Space-time may not be continuous but granular, built of discrete units at the Planck scale. If so, then perhaps loopholes exist, tiny cracks through which faster-than-light travel might slip. Quantum entanglement already teases us with its strange instantaneous correlations, though no information can yet be transmitted this way. Still, the hint remains. The universe may contain connections that ignore distance altogether. Even if these cracks exist, exploiting them may require energies beyond comprehension. To probe the Planck scale would mean colliding particles with powers trillions of times greater than our largest accelerators. For us it is impossible, but for a future civilization or for intelligence elsewhere, perhaps it is not. And if they can cross such thresholds, the horizons that confine us may be open to them. This possibility forces us to revisit one of the most persistent mysteries of our time, the silence of the cosmos. If advanced civilizations can reach the far side of the universe, or even leap between universes, why do we not see evidence of them? Where are the travelers, the signals, the artifacts? This is the Fermi paradox sharpened by our own dreams of cosmic travel. If the road exists, why does no one walk it? There are many possible answers. Perhaps the road does not exist and we are chasing illusions. Perhaps civilizations destroy themselves before they can attempt the journey. Or perhaps they do walk it, but in ways we cannot perceive. If wormholes or higher dimensions are their highways, their traffic may pass unseen. Their traces hidden in physics we do not yet understand. We may be like ants watching a superhighway, unable to recognize the vehicles that pass overhead. But another possibility is more unsettling. Maybe the silence is intentional. Perhaps advanced civilizations discover that horizons are not meant to be crossed. Perhaps they learn truths so dangerous that they retreat, choosing isolation over expansion. If the universe is structured to resist travel to its far side, then attempting to break those rules may unleash consequences that no intelligence is willing to risk. The absence of travelers may not be proof of impossibility, but proof of wisdom. Still, humanity is not wise in this way. We are restless. We test boundaries even when warned. We push forward even when failure is certain. That impulse has carried us from caves to continents, from Earth to the moon, from radio silence to signals spanning light years. It will carry us further still. Even if the other side of the universe is unreachable, we will try, and in trying we will discover new truths as we always have. Every frontier humanity has faced has eventually fallen. Mountains have been climbed, oceans crossed, skies conquered, and even the moon has felt the imprint of our boots. Each time the impossible yielded to determination and discovery. But the cosmic horizon is unlike any frontier before. It is not a barrier of distance or danger, but of law. To cross it requires not more fuel or stronger ships, but new physics. And that raises an uncomfortable possibility. What if the laws are final? This possibility confronts us with humility. The universe may not be designed to accommodate travellers. It may not care about our longing to reach the far side. Our species may be confined forever to a local bubble, a cosmic village surrounded by walls of light and expansion. For some, this is a bleak vision, a cosmic prison that denies us our destiny. But for others, it is a call to look inward to find meaning not in conquering horizons, but in understanding the space we already inhabit. Still, resignation does not come easily. Even if we cannot cross, we can learn. The universe may be vast beyond reach, but it is not beyond comprehension. Every photon captured by our telescopes, every ripple recorded by our detectors, every particle smashed in our colliders is a clue. Piece by piece, we reconstruct a picture of the whole. The far side becomes knowable even if it remains untouchable. And in this effort, something remarkable happens. We begin to glimpse not just the structure of the cosmos, but its story. We see how galaxies formed, how stars lived and died, how elements were forged in stellar furnaces. We trace the arc of cosmic history from the Big Bang to today. We even predict its future, imagining the heat death, or the big rip, the slow fade, or the violent end. The other side of the universe, then, is not merely a place. It is a narrative one that we are slowly learning to read, but knowledge does not erase mystery. For every answer, new questions appear. Why does dark energy exist? What is the true nature of time? Do dimensions beyond our perception shape the cosmos? Does the multiverse stretch infinitely with other realities pressing against our own? These are not idle speculations. They are the very questions that arise when we try to imagine what lies beyond our horizon. Perhaps the far side of the universe is not something to be travelled to, but something to be explained. Perhaps the true journey is intellectual, not physical. The act of asking the question forces us to develop new theories, new technologies, new ways of seeing. Already that impulse has given us relativity, quantum mechanics, and cosmology itself. Who knows what it will give us next? Still, we are human, and imagination will not rest. We dream of ships that ride the warp of space of wormholes stabilized by exotic energy of gateways to other universes. We dream because to stop dreaming is to stop being human, and maybe that dreaming itself is the bridge. We may never build the road with matter, but we build it with thought, with stories, with wonder. In this way, the unreachable far side is already shaping us. It compels us to push beyond limits, to wrestle with paradoxes, to embrace mysteries. It teaches us that horizons are not only obstacles but mirrors. They reflect our longing, our determination, our refusal to accept confinement. The other side may remain forever hidden, but in striving for it we become something more than what we were. To imagine the other side of the universe is to wrestle with paradox. On the one hand, physics insists that horizons are final, that light speed and expansion define what is possible. On the other hand, human curiosity refuses finality. We stand at the edge of what we can see, gazing into darkness, convinced that if there is a beyond, then one day we must reach it. This tension is not a weakness. It is the fire of discovery. We must remember that many boundaries once thought absolute have fallen. The sound barrier was once believed unbreakable. The energy required to leave Earth seemed impossible until rockets turned theory into reality. Even the atom, once considered indivisible, yielded secrets when we dared to probe deeper. Perhaps the cosmic horizon too will one day prove less absolute than it appears. But even if it does not, even if the horizon remains eternal, its existence gives us something of equal value. Perspective. By confronting our limits, we gain humility. We see how small we are compared to the cosmos, how brief our lives are compared to cosmic time, how fragile our planet is compared to infinite space. Yet humility does not diminish us. It sharpens our appreciation for the extraordinary fact that we exist at all. There is also irony here. The very limits that deny us travel to the far side are the same limits that allow us to be If the speed of light were not finite, stars could not shine as they do. If dark energy did not exist, galaxies might never have formed in the balance we observe. The prison is also the nursery. The horizon that confines us is the same horizon that made us possible. Still we hunger for more. The question what lies beyond is not merely scientific, it is philosophical, even spiritual. It forces us to confront meaning itself. If the universe is infinite, then the other side is endless repetition, galaxies stretching without limit. If it is finite, then the other side may loop back upon itself, erasing the idea of edges altogether. And if there are multiverses, then the other side is not just different, it is alien beyond imagination. In each scenario, the message is the same. The cosmos is larger than us, larger than our hopes, larger than our fears. And yet it is also accessible through thought. Though our ships may never reach the far side, our minds already have. In equations, in models, in stories, we have crossed horizons many times. That act alone transforms the unreachable into something intimate, something that lives within us. Consider again the cosmic microwave background, that ancient wall of light. It is the farthest we can see, but it is also the closest we have ever come to the origin of time. From its faint ripples, we have deduced the age of the universe, its shape, its fate. In those patterns, the echo of the far side is already present. The universe may hide its edges, but it does not hide its story. It whispers it in radiation, in gravity, in the very elements of our bodies forged in ancient stars. The more we learn, the clearer the paradox becomes. The far side of the universe is unreachable, but it is not unknowable. It is forever beyond travel, but not beyond understanding. We cannot step across the horizon, but we can extend our minds beyond it. And perhaps that is the deeper journey. Not physical conquest, but intellectual transcendence. And yet a question lingers. What if knowledge is not enough? What if humanity demands more than understanding? What if we demand presence, contact, experience? Will we ever accept that some horizons are final? Or will we keep building theories and ships, always straining toward an ocean we cannot cross? We began with a simple but haunting question. Could we ever travel to the other side of the universe? Along the way, we encountered the speed of light, the expanding fabric of space, the mysteries of wormholes, the whispers of the quantum foam, and the silence of horizons. Each path offered possibility, and each path demanded a price too great for us to pay. The dream remains beyond our reach, but perhaps the true meaning of the question was never about arrival. It was always about the pursuit. The universe is not cruel, it is indifferent. Yet in that indifference lies wonder. For out of blind laws and cosmic forces, beings have emerged who can ask, who can dream, who can long for the impossible. We are creatures of limits, yet we imagine the limitless. That act alone changes everything. The horizon may confine our bodies, but it cannot confine our minds. As we reflect, we realize that the far side of the universe is not a place. It is a mirror. It shows us who we are when confronted with the unreachable. Do we surrender content with what is near? Or do we reach anyway, knowing we may never arrive? History tells us the answer. We reach always. Even when the stars were just points of light, we dreamed of touching them. Even when the oceans were endless, we set sail. Even when the atom was indivisible, we split it. Horizons inspire not by yielding, but by resisting. Perhaps then the greatest gift of the other side is not that it can be crossed, but that it cannot. Its refusal shapes us, pushing us to invent, to question, to imagine. In trying to reach it, we uncover new laws of physics, new visions of reality. In chasing it, we build telescopes that capture the faintest echoes of creation detectors, that hear the vibrations of space-time theories that reveal the hidden structure of existence. Every step forward, even without arrival, expands our universe within. Still we dare to wonder about futures we will not see. Perhaps in some distant age, minds far beyond ours will master dark energy, sculpt space-time, and tame the horizons. Perhaps they will cross into the far side, stepping into regions forever hidden from us. If so, they will carry with them not only their own ambitions, but our legacy. The first questions, the first attempts, the stubborn refusal to accept confinement. We are the beginning of that journey, even if we are not its end. And if no one ever crosses, if the far side remains eternally sealed, then it still serves its purpose. It teaches us humility, and wonder shows us the grandeur of what lies beyond reach, and reminds us that meaning is not found only in destinations. Meaning is found in the striving itself. So could we travel to the other side of the universe? The honest answer is no. not with rockets, not with wormholes, not with any technology we can conceive. But could we imagine it, describe it, infer it, dream it? Yes, and in doing so we already cross a greater distance. The gulf between ignorance and knowledge, between silence and wonder. Let us then keep reaching. Let us keep asking, for the far side of the universe is not the end of our story. It is the beginning of our endless curiosity. And perhaps that curiosity itself is the true bridge, the one horizon we will never stop crossing.